I'm sorry, I'm yelling. Yes, now you're quiet. Thank you. Good morning. I hope everyone had a lot of fun at the pub quiz last night. Welcome back at the third day of Rocky Worlds. So I'm your chair this morning, where we have all kinds of talks about formation. And our first talk is by Paolo Sossi, who is a professor at ETH. And he will talk about homogeneous accretion of the Earth in the inner solar system.
Okay, thank you very much, and thanks for having me. For those first. So I was talking about how much total, so something about Earth's accretion and the future of the relationship on Earth's clock. So
Thank you very much. Questions for Paula? Yes, over there.
Floris van der Tuin. What about Mars?
What about Mars? What's the question?
Yeah.
Over there.
Okay. Yeah. So Mars. So that lies entirely within the NC field. I didn't talk too much about it. Yeah. Essentially, if we can go back to these figures. So Mars is sort of in the middle, and this is the interesting thing about Mars is that it's always in the middle of the ordinary chondrites, so where it says HLLL and EL and EH. And it's roughly equidistant between those two bodies, again, for all of these different isotopic systems. And so it's not necessary, again, also for Mars, that there's any sort of exotic carbonaceous component either. So this is perhaps more intuitive, because if we think that in the old paradigm where you think that the Earth has more carbonaceous material than Mars does, it poses a bit of a dynamical challenge for these sort of pebble accretion models or even planetesimal model, because somehow you have to get supposed outer solar system material above or across or through Mars and preferentially accreted to the Earth, which may be done in some sort of contrived way, but I think this is perhaps a more readily explicable scenario. So, yeah.
I'm afraid we have to leave it here. So other questions will have to wait for the break. So let's, sorry?
Or on Discord.
Or on Discord, yes. So can I invite the next speaker? And have another round of applause. So our next speaker is my office neighbor, Melissa McClure from Leiden Observatory. And the title of her talk is Forged in Fire, Revealing the Start of Rocky Planet Formation in Embedded Disks. Go ahead.
Perfect. Okay, everyone can hear me. Awesome. I'm really excited to be able to talk with you guys today at this great conference that combines so many fields that are really relevant to what I'm about to show you. Is it possible to maybe lower the lights a little bit? But so as we've seen over the last few days, there's a number of topics that are related to each other that are really critical to the rocky planet formation community, rocky planets community. And that's where, when, and how did Earth form in our solar system, and do other rocky planets form similarly in the same way as Earth? And I think a number of other speakers have addressed this already from both a theory perspective and also a solar system perspective, but I'll focus on the when and the where with respect to astrophysical settings. So as we saw yesterday, in our own solar system, the planet formation timeline has the first generation of iron-rich planetesimals form very, very early. Within about 0.3 million years of the t=0 moment for planet formation of this timeline. Now, this t=0 moment is measured from the condensation of highly refractory minerals in the form of calcium aluminum rich inclusions, which are the oldest solids in the solar system from radiometric age dating. These are sizes that would be counting as pebbles from the perspective of disk physics of less than 1 centimeter in size. But these are not the only refractory inclusions. There's another category that condenses from exactly the same isotopic reservoir as the CAIs, and those are the amoeboid olivine aggregates, or AOAs. It's a terrible name, terrible acronym. They're slightly smaller than CAIs, and instead of being formed of calcium and aluminum-rich materials, they're formed of 10-micron size forsterite crystals that are stuck together in an agglomerate. They're much more abundant than CAIs, but they don't have any age dating themselves. And if you see AOAs, because they come from the same isotopic reservoir, it implies that you would actually have CAI condensation likely already. Now, these materials must have condensed from very hot gas close to the central star. And most models of disk temperature structures assume sort of like a 1D temperature structure like this, where you have a silicate sublimation rim at the innermost radius, and then you might have like the water snowlight out at 2 AU. So there's not much room to actually condense these minerals. But actually, when you have a 2D temperature and density structure in a highly accreting embedded protostellar disk, you actually get a very different structure. You still have an innermost silicate sublimation rim at 0.1 AU, but the midplane is heated by viscous accretion heating. So it actually reaches the 1400 Kelvin temperature necessary to sublimate rocky minerals out to several AU in radius. So what happens is you bring in interstellar dust, including iron, like amorphous olivine, amorphous pyroxene. It gets sublimated in this region. You release elemental iron, magnesium, molecular oxygen, and SiO gas. And then that material either accretes onto the central star or is sent outwards through viscous spreading or in a disk plane to the outer part of the disk. And as it does that, it condenses these CAI-rich minerals here, and also the silicate, like AOA-rich minerals further out. Now, we can say from this, you cannot form a planet interior to this thermostat region because there's just not enough solids. You have to form the planet outside of the thermostat region. So therefore, the outer radius of this region regulates the formation of rocky planets in planetary systems. Now, if we consider now how the solar system timeline matches up with what we see in astrophysical settings, this is a plot from a review by Nittler and Tesla. It's thought that the CAI epoch and the iron-rich planetesimal formation epoch happen either during the class 0 or class 1. However, these are the protostellar, the embedded protostellar disk, as opposed to the class 2, which is regular protoplanetary disks. Now, however, the t=0 moment for the astrophysical timeline is measured from the first formation of the central star. So it could have a very different offset relative to the solar system timeline, and we don't know what this offset is right now. Unfortunately, for embedded disks, it's very difficult to see them because they are hidden inside their embedding envelopes and within clouds. So they sort of have a black box around them. You can't tell what this epoch is. However, there is a protostar that we observed recently with JWST, and it's the perfect analog for the sun at this early time. It has, it's in a clustered environment in Orion. It has a mass, or sorry, it has an age that's similar to the age we would expect this to happen at. It has a mass that's 0.6 solar masses with a mass accretion rate such that its mass will grow to 1 solar mass within 1 million years. And its disk is roughly equal to the minimum mass solar nebula in the solar system. So we observed this system with JWST, and you can see it has this gorgeous spectrum. Everything that looks like the sort of noisy hair is actually molecular bands in absorption, and they have so much information in them. You can also see here that there are sharp features in the 10 micron feature that correspond to crystalline silicates. So what can we learn from this system about this hot epoch in the early solar system? So first, because we see these lines in absorption, that must mean that they are backlit by a hot continuum source, which could be this thermostat region. Otherwise, we would see the lines in emission. Then if we look at do LTE models for the SiO gas band, it has a relatively cool temperature of about 500 Kelvin. And it also has, it's blue shifted by about 20 kilometers per second relative to the source. And from our models, it's coming from about 1 AU in radius. So this is for the gas. If we look at ALMA, just to see if we can get some confirmation about the kinematic components, we can see that the velocity that we have here for the infrared SiO, we don't see any component there in the ALMA spectra for this source, which means that even though there's SiO gas in the jet coming from it, it's not the same SiO that's traced in the infrared. The lack of detection of the SiO at the source in the 2D map indicates that the infrared SiO must be coming from a radius of less than 2.2 AU, which is consistent with what we got for our JWST models. So this gas is coming from the inner part of the disk within where we think Earth probably formed. Now, if we look at the minerals, we detect a number of different minerals, again, through these peaks in the 10 micron feature. Those are forsterite, enstatite, and silica, all in their crystalline forms. And critically, the ratio between the enstatite and the forsterite is 2.8 with 3 sigma uncertainties here. So this means that these crystalline silicates are likely condensing from this cooling SiO gas. And the scenario that we think we see is that As this gas moves out, some fraction of it is actually moving up vertically in the disk and cooling as it does so, leaving things like CAIs here and these crystalline silicates up here with the residual SiO gas left over. So what this means in terms of the mineralogy is as this gas cools near the midplane, if we had equilibrium condensation like you expect in the solar system, you would form the CAI minerals close to the midplane, form then the AOA minerals further up, and then so forsterite and enstatite at slightly cooler temperatures. And by 500 Kelvin, you would have no leftover SiO gas and no crystalline silica. You also have a much smaller enstatite to forsterite ratio of 0.5. But if we look at models for a different kind of condensation, partial isolation condensation, if you grow your condensates quickly enough, they actually decouple from the gas and they have a smaller surface area relative to their bulk center. And this means that you cannot have gas phase reactions between the gas and the surface be very effective at forming enstatite. So instead you directly condense enstatite, which lowers the ratio of magnesium to silicon in the gas phase and leaves leftover SiO gas, a higher enstatite fraction, and produces silica. So we think in this scenario, what we're actually seeing is essentially the formation of analogs to the CAIs and amoeboid olivine aggregates here. This is implicit, this is direct. So we're really seeing this first moment for formation. Now, one other really cool thing, this partial isolation condensation requires dust to gas ratios of greater than 10 times the ISM. And there are models for protoplanetary disks that show you can actually get dust to gas ratios about 400 times the ISM. So this means we really should have had the capability of forming a streaming instability in this disk potentially. Now we see some evidence that actually planetesimals may already have formed, because if we look at the ALMA data, there's less SiO in the jet than we would expect according to the amount of CO that we see. And we also have no iron in the jet in the mid-infrared. So all of this means we probably have formed planetesimals already, and this depletion is a signal of that. This is a cartoon, can form planetesimals here, can't there. We've seen this, and one final slide. This is not a single one-off source. We do actually see another one already. So this may be legitimately something that happens specifically to higher mass protostars or higher mass disks, like the sun and like these disks in Orion. So thank you very much. And if I went over too much, I can sing. Don't stop me now. I can do it.
Yeah, now I want you to keep going.
Don't stop me now.
Somebody filming this?
Oh yeah,
the YouTube.
Shit.
Sorry. Let's make some time for questions. I see a question over there.
Hi, Elisabeth van Koten, Starplan, University of Copenhagen. Thank you for your talk. So I was wondering if you can now place AOA formation on a class timeline, like you said, because we do have some ages for AOAs that are more contemporary with CAIs, we think. This is from Larsen et al., 2011, where they dated these AOAs together with a bunch of CAIs.
Where were you when I was writing that review section of the paper? Okay. So the question was on the timeline. Can we go back to the timeline?
So can you now match an age with a class 0 or a class 1?
So yes, I think in terms of this offset, I think we're closer to the intersection between the class 0 and 1 than to the start of the class 0. But the problem is when we only have this one source analyzed so far, that source is it has an average age that comes from statistics for class 0s and 1s, right? We don't have any kind of absolute measurement. So what we need to do is build up a sequence and observe more objects like it that appear to have indicators that suggest that they're forming earlier, that they're younger and younger than the previous ones. So this new source is actually based on some indicators like its bolometric temperature, it's even younger than the one that we already have. So I think once we get enough of these, then we can answer that question.
Thank you.
Thank you. I'm afraid we're really over time now, no matter how much I would like to see you sing. Let's thank for this second. So our next talk this morning is by Nader Hagegibur from the
Hear me now?
Planetary Science Institute and University of Hawaii. And he will talk about non-uniform protoplanetary disks, the most physical viable birthplace of terrestrial planets.
You hear me? Very good. So, I'm sorry.
down.
So down is next, and up, and that's the perfect. So, planet formation, right? Terrestrial planet formation. There are two facts about any planetary system that do not allow us to develop definitive planetary formation model for that system. One, we don't know the initial state of the disk that became the final product. Two, we don't know the dynamical evolution of that disk, the path that it took to become the final product. So this lack of knowledge of the initial state and dynamical history is a good thing and a bad thing. It's a good thing because it gives us a lot of freedom to come up with a lot of models. Is a bad thing because it gives us a lot of freedom to come with a lot of models. So, you know these models. This talk is not about those models. They have their ups and downs, the positive, negative, and everything. But the talk is not about that. The talk is about the following. Despite the fact that we cannot come up with a definitive model for formation of any planetary system, it is in fact possible to start from a state that is the outcome of the basic principles and let that state evolve on its own without us forcing it, evolve, and then do that many times, study the results statistically, and see what is the fundamental physics or the physical processes that explain characteristic of our system. That's the goal of planet formation. The goal of planet formation is not to come out and say that, how did Mars with 0.1 Earth mass form at 1.52 AU? The point of planet formation is what was the physics that resulted into a small mass at 1.52 AU? And that will allow us to generalize it to other extrasolar planetary systems as well. So how do we do that? We start from dust coagulation. So you all know dust coagulation, that dust particles are formed. Dust particles go through the process, any process that you want. Planetesimals, kilometer-sized bodies are formed. These are all based on fundamental physics. Growth of dust particles can be reproduced in laboratories. It's all basic principles. Formation of planetesimals is all basic principles. No matter what method you use, the disk of planetesimal will exist. And these planetesimals will go around, hit each other, and grow and grow and grow, and form planetary embryos. That is also basic principle. And these planetary embryos place themselves at the multiples of this thing that is usually called Minkowski radius. Okay, so this is all good, and it results in a disk, and that is the disk that we don't know is the structure. So we don't know the initial state, we don't know the structure of that disk. That disk is because the simulations are stochastic, that disk is a hush-wash of a lot of other things. It's a cartoon of it. That disk has voids and has cluster, and different objects of different properties and sizes are scattered all over the place. Some of them put themselves at certain distance, but in general, it's something random like this. This is the one that we don't know. So if we don't know this, how do we proceed? For the past 40 years, we have been getting around this lack of our knowledge by considering a proxy, by assuming, let's go here. So by assuming that all the mass in that disk is in planetary embryos, and then we put them in a specific distance next to each other, we go back to our simulations and identify the radial profile for the surface density. We applied that, and then we scatter a lot of planetesimals, and we say go. And this becomes a traditional model of terrestrial planet formation. This is all good, except that this simulation is extremely stochastic, which means you cannot just take them at face value. I'm deliberately showing something that does not work. You cannot take it at face value. You have to run many of them. So the question is, if you cannot take it at face value, what's the point of it? The point of these simulations is not to reproduce solar system. The point is to learn about the properties of solar system. We have learned a lot from where the source of the water is and why terrestrial planets in our solar system are interior to 2.1 AU, what is the structure of the asteroid belt. And we also noticed a lot of issues. There is issue with the mass of Mars. There is a decoupling between Earth and Venus is not on there, and the planets form in the asteroid belt, and a lot of other things. So somehow during the past 40 years, some people lost the sight of the fact that that thing, that is a proxy. It is not the actual disk. It is, we created that because we didn't know, right? And that's very important. It's a proxy to lack of our knowledge. They took that as being the real thing and then said that because there are all these problems, we have to throw out everything and come up with new models. So what I'm trying to promote, or I've been promoting for past several years, is that some of these are the result of using that proxy. So how do we solve a problem that we create? Just don't do it, right? So they come from using a proxy. Don't use proxy, use that. But we don't know what that structure is. However, there is something in there. We see a random distribution of voids. We see random distribution of objects. Planetesimal formation and growth is basic principle. So what do? Take a disk, any range that you want, and introduce clumps and objects of different sizes and voids randomly. But do that many times, thousands and thousands of times, and then run your simulations. That's what we have been doing. At the top, you see the traditional model, and at the bottom, we just introduce randomly clusters and voids. And we did that many times. To be honest with you, 2,000 times. And this is our initial condition. We did that 2,000 times, consider different radial distributions, and we say go. You want solar system? Here, that's your solar system, right? But like I said, these simulations are stochastic. You should not take them at face value. They give you a lot of other things, right? You have to study them statistically. So let's do that. Let's study them statistically. The first thing that we do is that homogeneous means the traditional model, and inhomogeneous means this clumpy thing. So as you see, the first thing is the model produces less planets with less mass. This is a good thing because the traditional model exaggerates mass. So we are moving forward. What I want you to see here is the mass at the place they were formed. First of all, ignore these. These are artifacts of the initial artifact of the edge effect. And ignore these. These are the asteroid belt. Again, those are artifacts. The focus has to be around this area, specifically there. You see that the traditional model doesn't give us enough mass, but the that when we use a clumpy disk, you get a lot of small mass, especially in the region of Mars. So it's addressing the Mars and Venus problem, and also is reducing mass of Earth to what is supposed to be, to closer value. Here, what I'm showing is the probability of occurrence of mass at different same major axes. Again, ignore these. These are artifacts. Ignore these. These are artifacts. Focus in this area. And as you see, when you don't use proxy and go back and use what could be the actual disk, then you fill up the probability. The probability increases for objects that are closer to what we see in our solar system. I want you to specifically look at this down here. I don't know if you see it back there. This is an orange thing appearing, showing that the probability of forming Mars increases. Sorry. And this is the way that we analyze it. Earth analogs, Venus analogs, Mars analogs, and it increases the probability of formation of Mars, addresses that, and also it gets the time of the formation of Earth and Mars and Venus closer to what it's supposed to be. Okay, so moon forming impact. It addresses that as well. This is the current understanding that we have for moon forming impact, 4.516, and the age of the solar system, 4.568. And if you do the math, the time of the moon forming impact after formation of CAIs is around 50, 55, close to 60 million years. And now you see that So you see that this clumpy approach gets the time of the moon forming impact closer to what it's supposed to be. So it gives you, this is all about the mechanics of it. I'm not including any chemistry or composition, anything. I just explained that if you don't do that proxy thing, but use some clumpy disk, you get the mechanics to work in your favor. Mars works out, Venus works out, time of moon forming impact. But what if, what about compounds and about the water and all that stuff? I cannot answer those now. The reason for it is that if you take the collision or growth to be perfect merging, I showed in 2022 that you exaggerate your mass and composition, water contact, any composition, you exaggerate it by up to about 40%. That is unacceptable, right? That is why that was one of the man-made problems, that there is too much water in these planets. So how do you do that? You must resolve collisions through SPH. You have to do that in order to be able to get the result to be quantitative. Now, here's the thing. How much time do I have? Okay, 3 seconds. So here is the thing. From those 2000 simulations, we have a good number of running on SPH. SPH simulations take about a year to run, okay? So I'm not going to finish this talk. I'm going to stop talking here. I'm not going to show you the conclusions. 2 years from now, in Rocky World 5, I'm going to pick up from here, finish this talk, and I get the gun. Thank you so much.
Hey, so
No, you can ask questions now.
wait for Rocky World 5 to ask. No. Quick question. Yes, in the back.
Hi, Christopher Monahan from the University of Montreal. Just from your sort of results slide, when you were comparing the uniform to the inhomogeneous model, you had the chance of a Venus analog being a little bit lower in the inhomogeneous model.
Right.
Of any concern, or is that just statistical?
No, it is the statistics. Let me go back to that. So once I get this stuff done, then the statistics of those masses and their numbers will improve as well. Yeah.
Okay. Another quick question. Okay, maybe I have one.
Sure.
Just as a this person. So how would we get this random distribution of planetesimals in the disk? Because right now we think that they form at specific locations due to snow lines or maybe infall. But to get them scattered throughout the disk, do you have an idea?
So what you're saying is what I mentioned at the beginning, that we don't know how they get scattered throughout the disk. Okay, so to mimic that scattering, the knowledge, to mimic what we don't know, we say instead of doing 1, do 1,000, but randomly scatter them everywhere. And then once you do a statistical analysis, you get closer to what it could have been.
Okay.
I don't know if I answered your question, but yeah.
Just trying to think how this translates to disk observation. But
very good. So disk observation will inform the distribution. So some of these distributions will not agree, some will agree, but then because you are doing several thousand of them, the statistical analysis will actually get rid of, you know what I'm saying? When you do the statistical analysis, the noise will go away and you get closer to what it's supposed to be. You will not arrive at the true value, but you get closer to what it's supposed to be.
thank you. Okay, then let's thank our speaker again and move to the our next speaker is Matt Roche from the University of Bristol. And he will convince us, so his conclusion is the title, that pre-lunar oceans shaped Earth's volatile budget. Matt, give it up.
Great. So hi, everyone. I'm Matt. I'm a final year PhD student at the University of Bristol. And I'm going to be telling you about some work that we've been doing looking at the role of giant impacts in shaping the volatile element chemistry of terrestrial planets. So we think the Earth acquired most of its volatile elements during the main stages of its accretion. And in this talk, I'm going to be thinking about the elements carbon, nitrogen, hydrogen, and the noble gases. And these elements in the bulk silica Earth, the accessible portion of the Earth, are certainly isotopically similar to a range of different chondritic sources, but their abundance ratios tell a slightly different story. So if we look at the carbon to nitrogen versus hydrogen to nitrogen ratios of a range of different potential building blocks for the Earth, we see the Earth plots all the way over here. It doesn't cluster within these. And so ultimately, something must have happened to the Earth's volatiles to result in this unique signature. And one possible explanation for this is giant impacts. And these are collisions between planet-sized bodies that mark the end of primary accretion. And we actually expect multiple giant impacts to take place onto the growing terrestrial planets. And it's now been shown in a wealth of previous studies that giant impacts can actually erode significant amounts of a planet's atmosphere. And therefore, they're able to remove a major reservoir from our planet. But there's one thing that all of these studies that I show here haven't really yet taken into account, and that is the effect of a surface ocean on your planet. And it's actually been shown that the proto-Earth itself likely hosted a liquid water ocean on its surface within tens of millions of years of the start of the solar system, as the planet sufficiently cooled and the impact energy flux slowly declined. And it turns out that an ocean can actually either enhance or inhibit the amount of atmosphere lost during a giant impact. And it's to do with this number R, which is the ratio of atmosphere mass to ocean mass. And it turns out that in the case where this number R is less than 1, so our ocean is more massive than the atmosphere, the ocean can actually act essentially as a big spring and help accelerate more of the overlying atmosphere to be lost. And so just to return to this idea that giant impacts could be responsible for fractionating our volatiles, it's been suggested that by losing different amounts of ocean relative to other reservoirs on the planet, we could generate some of these unique signatures. But ultimately, we need to know how much fractionation these impacts could be causing. And so what we did was run some new high-resolution smooth particle hydrodynamic simulations involving collisions onto a planet with both an ocean and an atmosphere for the first time. So what we're looking at here is a cutaway through the equators of the colliding bodies with the particles colored by their material types as shown. And this particular scenario is a collision between a roughly Earth mass planet with both an ocean and an atmosphere, and a roughly Mars mass impactor at an angle of around 45 degrees and at the mutual escape velocity of around 11 kilometers a second. And hopefully this is just helping you visualize a little easier just quite how violent these events are, and also the ease at which different material layers can be stripped off of a planet. So what we did was run a whole suite of these simulations, varying all the different combinations of impact angles and velocities to try and start building up an idea of the trends in how much atmosphere and ocean we can lose in different types of impacts. So what I'm showing here is a plot of atmospheric loss fraction on the y-axis versus impact parameter on the x. This is essentially angle, and just here I'm showing what an impact parameter of 0 versus 1 would look like. And this particular scenario is for an R value of 1. So our ocean and atmosphere are of equal mass. And what we find is that as we increase the impact angle, we decrease the amount of atmosphere that we lose. And the faster impacts in the brighter colors lose increasingly more atmosphere. But if we just pay attention to the difference between the solid and the dashed lines, so the solid lines being the cases where our planet had both an atmosphere and an ocean, the dashed being the case where the planet had only an atmosphere. Here we see the ocean makes relatively little difference to the amount of atmosphere that we lose. But if we consider the case where the ocean is 10 times as massive as the atmosphere, we can see the ocean can actually significantly enhance the amount of atmosphere lost, and in some cases cause maybe an additional 20% or so loss. And we can also look at how much ocean is lost for the first time. And ocean loss is much less efficient than atmosphere loss. And even in the most extreme scenario we simulated, maybe around 50% of the ocean was lost, but generally this value is much lower than this. So we've now got some idea of how much atmosphere and ocean we can lose in different types of impact. What we want to know is what that translates to in terms of a degree of fractionation. And so I'm just going to focus on what's happening to nitrogen and hydrogen here to start. So I've got the nitrogen-hydrogen ratio on the y-axis there, and I'm going to assume that all of the planet's nitrogen is in the atmosphere, all of the hydrogen in the ocean. And in this particular scenario, that Earth accreted all of its volatiles from a carbonaceous chondrite. And we want to see what our individual impacts can do to lowering this ratio. And what we find is that individual impacts can certainly lower this ratio by quite a lot, and in some cases down to what we measure for the bulk silica Earth in one go. But since we only know for sure that the Earth experienced one giant impact, the one that formed the moon, if we highlight a few of the cases that are akin to two different moon formation scenarios, these individual impacts don't get us down quite far enough, which could possibly be evidence that the Earth experienced at least one additional giant impact earlier in its history. But we can actually learn a little more by considering the combined fractionation of nitrogen, hydrogen, and carbon as well. So now I'm showing the nitrogen-hydrogen ratio versus carbon-to-hydrogen ratio, again assuming that the Earth accreted all of its volatiles from a carbonaceous chondrite, and I'm going to assume something about partitioning of nitrogen and hydrogen into the interior as well. And what we can do now is look at what sequences of giant impacts do to altering this starting ratio after 1, 2, and 3 giant impacts. And you can see here that I've just applied exactly the same impact in the sequence. And we can do this for all of the different impacts that we simulated and start to sort of map out this parameter space in which we can move, whether that's either towards or away from the bulk silica Earth. But we can actually go a step further than this, and rather than taking the simple scenario of selecting all the same impacts each time and making some assumptions about the partitioning, if we run a Monte Carlo simulation that does all of this randomly selecting impacts and partitioning, we come up with something like this. And this is just the results after 3 giant impacts. It looks very similar for 2 giant impacts, and the color is showing the frequency of how many of those events lie in this portion of the parameter space. And it's possible that giant impacts alone could get us to the bulk silica Earth. No doubt there's other mechanisms taking place like core formation, but ultimately this is really exciting that we've shown what giant impacts can do to our volatile chemistry here. And so just to try and summarize all of this, we've shown using some new high resolution simulations that oceans can substantially enhance the amount of atmosphere loss during a giant impact. And they can also cause significant volatile fractionation by enhancing the loss of carbon and nitrogen from the atmosphere, whilst largely retaining hydrogen in the ocean. And it's possible that multiple giant impacts onto an ocean-bearing Earth could be responsible for the bulk silica Earth's distinct volatile chemistry. And ultimately, it was the differences in the timing, sequence, and style of impacts that could account for the diversity in the planetary volatile inventories that we see both within our own solar system and also beyond. And just before I finish, I'd like to point out this paper of mine that came out last year, also focusing on atmospheric loss during giant impacts, where we present a new scaling law to predict how much atmosphere can be lost in different types of impact. And then just before I finish, I'm finishing my PhD in a few months and looking for postdoc positions, so I'd love to hear from you if you have any positions or funding or anything. So thanks a lot for listening.
Thank you for staying on time. Sad not to see you sing. Plenty of time for questions. Let's start here in the front and then we go to the back.
Will I wait for my
Yeah, please. For people online, it will be impossible.
Oh, thank you for the great talk. I was wondering, do any of your simulations predict significant amount of silicate, rocky material, crustal material being eroded at the same time?
So generally, all of the even the most extreme simulations or scenarios rather, eroded maybe no more than about 15% at most of the mantle. So not a lot, basically.
Yeah, over there. Yeah, sorry. First Nader, then Paul.
So I apologize. This is going to be technical questions. In one of your simulations, you showed that your impactee had a layer of ocean on top of it. So I was wondering how you did that in your SPH.
How do we what?
How did you did that with your SPH code? How did you put a layer of water on top? So like I said, this is a technical question. So how did you put a layer of water on top of a solid object and incorporated that into your equation state of your SPH code?
So, well, we have equations of state for all of the necessary materials.
Did you consider different layers on top of each other, or?
Yeah, so we've got core layer, mantle layer, ocean layer, atmosphere layer. We use the WOMA codes to generate our interior profiles, and it's relatively simple
Okay,
to do so. But
I'll talk to you else.
yeah.
Yeah, Paolo Tossi from ETH Zurich. So the E/H ratio, have you considered how that is influenced by this process? And a second follow-up, is the loss rate sensitive to the molar mass of the background gas that you assume in your uppermost layer?
So I'll start with the second one first, if that's all right. So in the scenario where we have an ocean and an atmosphere, the loss is relatively insensitive to what the atmosphere is made of. When we don't have an ocean, heavier gases are less easily lost. So in this scenario, it doesn't matter too much. We've not necessarily looked at D/H ratio. From speaking to various people, they seem to think that D/H will change when you sneeze on it, let alone if you hit it with a giant impact. So I'm not sure how useful that could be, but it's certainly something to think about. But
We should know D/H.
Okay, I'm sorry, we have to leave it here. So for the question over there, please find Matt in the break. So let's give another round of applause for Matt. So our next speaker is Hugo Pellissard from the University of Bordeaux. And he will revisit rocky planets, cooling phase, and magma ocean occurrence with a consistent atmospheric model.
Yeah, so hello everyone, my name is Hugo Pellissard. I'm a PhD student in Bordeaux in France. And today I'm going to talk to you about revisiting atmospheres and ocean formation on rocky planets. And especially I'm going to talk to you about the classical Earth and Venus dichotomy. So as you know, the Earth and Venus are very similar in terms of geophysical properties. They both start in the initial state as a magma ocean, but they end up very differently. For instance, the Earth gets an ocean on the surface, and for Venus, it's a very hellish environment. So what we want to know is how and why, and what can this case could teach us about the inner edge of the habitable zone, and yeah. And the question I want to address today is to what extent of water remains in the Venus mantle today, by using a self-consistent atmospheric model. So I'll go very quickly about the formation because you heard a lot about it and more clearer than me. So the planet formed inside a protoplanetary disk. And because of accretional heating, core formation, and radiogenic heating, the planet is very hot. It accumulates a lot of energy. So it's basically partially or fully magma ocean state at the end of planetary formation. And all this energy that accumulated inside the mantle needs to evacuate it to space in order to reach the steady state with the incoming stellar flux. And so for that, there is convection inside the mantle to bring the energy and the matter from the bottom to the top. And then the energy is radiated to space from the atmospheres. So basically, I developed a Python framework in order to couple an interior model with a 1D self-consistent atmospheric model ExoK that has been designed by Jérémy Lecomte. And so in the interior code, I coded myself using the Lebrun equation from 2013. And so the main assumption in the internal model is that during the cooling, the mantle will solidificate from the bottom to the to the surface. And so we're considering a magma ocean state, a mush state, and a solid phase. And the volatiles that are inside the mantle, during the solidification, they are migrating from the solid to the liquid state. And once the saturation is reached in the melt, the gas bubbles exhaust, then rise toward the surface and form the atmosphere. So I also consider atmospheric escape in order to quantify the amount of water that remains in the mantle, basically. And also, if the planet cools sufficiently enough, it may condensate the atmosphere and form an ocean on the surface. So it relies on the very famous concept of runaway greenhouse. So imagine you have a water ocean planet. If you increase the surface temperature, you will have more wet water vapor in the atmospheres, and you will increase the greenhouse effect. And then you start a positive feedback loop, and then you evaporate all the water in the atmospheres. And basically what we want to know is the opposite way when we cool, and if we reach a threshold in flux where we can condensate the whole water vapor into an ocean. And so now I will review like the standard scenario of Earth cooling proposed by Amano in 2013. So basically, Amano calculated that the steady state is calculated. I mean, the solidification is reached after 1 million years, with the ocean condensation shortly after formed, and that the atmospheric escape plays a really negligible role for the water inventory. And so we can see that we have a substantial amount of water retained within the mantle. Now, for the Venus scenario, Amano calculated that after 1 million years, we still have a magma ocean state when we reached the equilibrium state. And in order to cool again from this magma ocean state, we need atmospheric escape. And atmospheric escape will remove progressively water from the mantle. And basically, it will dry the mantle over 100 million years until we can actually solidify the mantle. So both of these scenarios relies on the very strong hypothesis, which is the fully convective atmospheric assumption. It's very strong because you can actually have the, the full thermal profile inside the atmospheres. However, it has been shown, recent publication by Celsius in 2023 showed that for really dense steam atmospheres, this assumption is wrong. And actually, when we do the calculation, we have this red line curve, which show that we no longer have this convective feature deep in the atmospheres. And so we have very different temperature surface temperature, and that could have really strong consequence for both of the scenario I presented just before for Venus case. And so I ran my model using the self-consistent atmospheric model to see if there is difference for the Venus case between Amano and my results. And what I can see is that we have lower potential temperature and lower surface temperature than what in the Amano work for Venus. Also for here I represented all the atmospheric profile converged during the interior evolution. And what we can see that after 1 million years of evolution of the interior, we can see that in the deep atmosphere, we are losing the convective features, and we have surface temperature that is lower than previously calculated by Amano. And I also look at the water inventory in the mantle over time. And basically in Amano, we have this red curve here. And for my work, what we can see that basically we retain more water inside the mantle at the end of the crystallization. However, this is still preliminary result that needs to be compared with a fully convective atmospheric profile in my code to see if it's consistent. And to summarize both of the scenario for Venus, so in red, this is the Amano case, and in blue, this is my work. So basically in the Amano case, you have still a magma ocean at the steady state. And so you lose a lot of water until 100 million years when you reach solidification. And however, what I propose in my work is that we reach like quickly the solidus, and that actually we preserve more water inside the mantle, and that at the end, well, we have still a bit more water inside the mantle. So yeah, I let you with my conclusion slide. So thank you for your attention. And yeah, I'm also looking for a postdoc position. So if you have one, don't hesitate to reach me in the coffee break. And so thank you.
Thank you for staying on that. Yeah, I see a question there.
Thank you for the talk. I was wondering then, under your model, it looks like you came to the conclusion the evolution of Venus was quite similar to the Earth. So do you have an answer for why it comes out to be such a different planet?
Yeah, so because it's still preliminary, I still have to check some physical parameters, for instance, like the inertial thermal cooling that I need to check. And yeah, so that's yeah.
Okay, we have a question online. And then we move on. Oh.
Yeah, hi. The question is, why does the convective profile break down closer to the surface?
Sorry, what?
Why does the convective profile break down closer to the surface?
No, I don't get it, sorry.
So the convective profile which you showed, these two temperature profiles.
This one?
No, I think, yes, this one. So why does it break down closer to the surface? Yeah, so what's the difference between the two profiles? I think that's the question.
The difference between this one and this one?
The black one and the red one, yeah.
The black and the red?
Yeah.
Okay, so the black one is the black curve is the hypothesis that the atmosphere is fully convective. So we just have a dry adiabat here, and here a moist adiabat. And the red curve is basically when you ensure that every layer of the atmosphere is thermally equilibrated. And so when you calculate it, you have this kind of profile, and that's why it's different. Yeah. I don't know if
one more question here, and I'm afraid that's we're done. Yeah.
Hi, Takamasik, Oxford. So as you know, previous work by Martin Turbet has shown that Venus's climate evolution is dependent on its initial conditions. So can you discuss a little bit the impact of initial conditions on your model results?
Well, actually, the initial condition of my model is basically the same as Amano in 2013, because the idea was really to compare both the work of Amano and mine just by using a self-consistent atmospheric model. That's the whole idea. So behind the rest, like the interior model and everything else is basically the same as what did Amano. The only difference is to use a self-consistent model. Yeah. So thanks.
Okay, let's thank Hugo again. And then we'll welcome our next speaker. Note that this is not our last speaker before the break, because you may have noticed that the first speaker was missing in the beginning, but he will give a talk at the very end. But our speaker right now is Nathan McGregor, University of Central, who will talk about linking the atmospheric and bulk composition and secondary atmospheres through novel meteorite outgassing experiments. So we have another lab talk.
Great. Thank you very much. Morning, everyone. I'm Nathan. I'm a PhD candidate at University of California, Santa Cruz. Today, I'll be sharing our results from some meteorite outgassing experiments that I've been working on in collaboration with Maggie Thompson, who many of you may know, my advisor, Miriam Tellis, and Laura Schaefer, and then Matresa and Mia were the undergrads in our lab who helped with this project. So atmospheric spectra is one of the main ways that we can probe rocky exoplanetary interiors and get an idea of what might be the composition of these rocky exoplanets. And that is because there is a link, right, that we've seen between the composition of the planet that went into forming the planet itself, wherein the material that formed the planet contained the volatiles that were later outgassed that formed the secondary atmospheres that we're able to observe today. And the outgassing processes that occurred from that include magma oceans, impactors, and volcanism. And so there's a connection between the material that accreted to form these exoplanets that we're able to observe and the secondary atmospheres that they outgassed. So if we want to get an idea in terms of developing this connection between those two properties, we can start with material that we are familiar with that formed our own solar system. So our planets formed from material that was similar in composition to chondritic meteorites. I have a picture of one here of a chondritic meteorite, right? They're just primitive stony meteorites, rich in volatiles and metals. Three main groups, sensitites, ordinaries, and carbonaceous, all of which we explore. And so the main goal of our work has been trying to establish some sort of link and provide data to modelers to get an idea of what these rocky exoplanetary interiors may be composed of based on the secondary atmospheres that we're able to observe. So here is our instrumentation. Our setup is brand new. It's a novel technique that is the only one being used in the United States currently for this kind of work. It consists of two instruments. The first is a thermogravimetric analyzer, a TGA, which is essentially just a balance in a furnace that allows us to melt the meteorites down and measure their mass loss very precisely. On the left, we have a microgas chromatograph, which is just a chromatograph with different columns in them that as the volatiles are outgassed from the meteorites, they move through the columns and we're able to detect them based on how they move through those columns. They're connected by this transfer line that we keep at 80 degrees Celsius to prevent any kind of condensation of the volatiles as they're moved from the TGA to the micro GC. We can use a variety of carrier gases that collect the volatiles and move them to the chromatograph. We can use oxygen, nitrogen. In this case, we used argon, and we conducted our experiments at 1 atmosphere. And we powdered our samples. Our samples are about 70 milligrams in size, so very small, about the size of a pea. For our ensitite, we used AB. For our ordinary chondrite, we used Krimka. And then for our carbonaceous chondrite, we used Murchison. So our technique consists of 3 steps. First, we powder the samples, like I mentioned. And then we put them in a 12-hour vacuum bakeout at 50 degrees Celsius to try to eliminate any kind of terrestrial contamination, since all of our samples are falls. And then we put them in the TGA, and then we have a 3-step heating process. So we have an initial ramp from room temperature up to 200 degrees Celsius. And we hold it at 200 degrees for 5 hours to further reduce any kind of terrestrial contamination that might be on the samples. And then we have a second ramp from 200 to 1450 Celsius. And it's in this area that we're going to be limiting most of our analysis, because prior to 200, most of that we can assume is terrestrial contamination, but anything between 200 and 1450 is indigenous to the chondritic meteorites themselves. So we can look at our results. So one unique thing about our TGA is we can actually look at the heat flow into and out of the sample. And so I plotted the heat flow on the y-axis here over the entire heating run here. Our ensitite is always in green, our ordinary is in orange, and our carbonaceous is always in blue. You can see all 3 exhibit pretty similar trends where they're decomposing throughout the heating process. But towards the end here, you notice this unique curve down. And that is where we're starting to see melting. And so the technique that we use allows us to not only see when melting is occurring, but we can assess what kind of outgassing is occurring prior to melting, during melting, and then after melting. We can also look at the mass loss, like I mentioned. And so here I plot the mass loss as a weight % on the y-axis over that heating run again. We can see the carbonaceous exhibited the greatest amount of mass loss, which makes sense considering it's more primitive, wet, has a lot more volatiles. Lost about 13% of its mass overall, compared to the ordinary, which is about 2.5%, and the ensitite, which lost about 1%. You can see the mass loss under 200 we associate with terrestrial contamination. So even though we did a bakeout, we still did not get all that out of there. And so this is we attribute to terrestrial contamination, and this kind of mass loss is what we associate with the actual volatiles indigenous to the chondritic meteorites. What we can do is we can take the derivative of that mass loss curve you just saw, and that gives us a rate. And so now we're looking at the loss rate on a logarithmic scale in units of micrograms per Celsius. And the reason this is useful is, as you'll see in the next slide, is we can then look at the outgas species as a function of loss rate to see how much is being lost at each temperature. And it's a much better and informative way of looking at it than just relative abundance. Because you might be seeing a lot of water earlier on, which we see, but less like hydrogen or sulfur dioxide. So here's the outgassing results for AB. This is our encetype. Again, you'll have mass loss on the y-axis overall, and then our heating run on the x-axis. You can see for AB, not surprising, we see a lot of reduced species being outgassed. We see nitrogen coming out quite early and quickly. We see CO2 early. The encetype that we have outgassed the most nitrogen of any of our chondritic meteorites. We see a little bit of water showing up at higher temperatures. The encetype that we used had the least amount of water of any of the chondritic meteorites, which makes sense considering it's an encetype. We see as it gets higher and it's hotter, we start to see hydrogen starting to peak up more. It's being released throughout, but it starts to pick up, and we start to see hydrogen being released later at higher temperatures. Also unique to our encetype outgassing is this unique CO curve. So from about 800 to 1200 Celsius, you see this peak of carbon monoxide. And that was pretty unique to just our encetype. For ordinary chondrite, which is Krimka, you can see a lot of water being outgassed very early and continuing it throughout the run. We see carbon dioxide coming out pretty early as well, and then most of that kind of dropping off by about 1000 Celsius. And then similarly, we start to see an uptick in hydrogen. This doesn't start to outgas hydrogen until higher temperatures, but a noticeable uptick as we get to higher temperatures in hydrogen. We see nitrogens kind of hanging out throughout, not to the level of the encetype. And the two distinguishing features for the ordinary chondrite is we have no carbon monoxide. So the ordinary chondrite did not release any kind of carbon monoxide, so it didn't have the kind of unique, neat peak that we had with the encetype. And also we start to see SO2 outgas. So as the sample starts to melt, we start to see SO2 starting to come out at these higher temperatures. That was unique to Krimka compared to our ordinary chondrite, or I'm sorry, our encetype chondrite. And then finally, we have our carbonaceous chondrite Murchison. And unsurprisingly, you can see a lot of water and CO2 being outgassed very early, a significant amount. We see hydrogen being outgassed throughout the entire temperature evolution as it's being heated, with a noticeable uptick at the end again, but also just a significant amount of hydrogen coming out very early. We see CO being produced pretty much the entire heating run. And we also see that same kind of uptick in SO2 at high temperatures. So as the sample is getting close to melting, we see this increase in SO2 that continues to the end of the heating run. And so the carbonaceous chondrite we had the greatest diversity of volatiles, but also the greatest total abundance of volatiles that we outgassed. So our work also offers a unique way to quantify departures from equilibrium during outgassing. And the way we look at that is we look at the fugacity that we can calculate from our experimental results. So what I have here is the results for AB only for now. And so on the y-axis, I have the fugacity plotted relative to the iron Wüsteit buffer. So the buffer is here at 0. Anything above is more oxidizing. Anything below is more reducing. We took the ratio of the hydrogen and water to form this dotted, this dash curve here. We took CO2 to CO from our experimental data to form this curve. And then Laura Schaefer ran an equilibrium model here that we have as a solid curve. And you can see that if these curves are at equilibrium, they'd be closer down here and plotting on this curve. But since our experiments are not at equilibrium, since we're having active outgassing and the volatile species are being carried away, this offers a way to actually quantify that departure from equilibrium. But one of the trends that we've observed is that as you get to higher temperatures, the curves start to approach that equilibrium trend. And we see this as well with our Krimka data. Again, we can't plot the CO2-CO curve for Krimka because it didn't outgas any CO. But we can do it for water and hydrogen. And you can see there's a departure in lower temperatures to moderate temperatures and a trend towards equilibrium at higher temperatures. And then finally, we can look at Murchison. And so here we have Murchison, the model, equilibrium, and solid curve, and then our two experimental curves that track the trend pretty well and continue to kind of hover near it throughout the outgassing and approaching equilibrium at higher temperatures. And with that, I'll leave up my summary slide and look forward to any questions. Thank you very much for your time.
You? Okay, lots of questions. Let's start here.
Hi, Francesca Mialzi, ETH Zurich. Thank you very much for your talk. I was wondering if you have a sense of what are the mineralogical reservoir of the species you're seeing, and if you're concerned that the speciation you're seeing is affected by your temperature. Specifically, if these things are contained in, for example, fluid inclusions, I would expect your temperature to affect speciation. So I was wondering if you have a comment on these, and if you think they are solutes in mineralogical phases or like fluid inclusions.
Right. And so we think of many of the gases are housed in certain mineralogical phases, partly because if you look at these curves, these kind of peaks here that you see, we associate with mostly some sort of mineral decomposition process that's happening. And that's actually work that we're going to be looking at in the future as we've started looking at the samples and residues in the SEM and EDS to look at the mineralogy to see what host phases might host these different gas species. But that is something that we're looking at. I mean, certainly like Murchison, it's rich in like clays and phyllosilicates. And so that's going to be housing a lot of the species that we're seeing that are being released, especially at early temperatures. So for like Murchison, this early kind of decomposition that's happening that's releasing a lot of this water and CO2, we can certainly associate with like phyllosilicates, wet clays, organics. Similarly for the Krimka, similar where it has, we can associate some of those earlier things with that. The SO2, that's we're kind of looking at a little bit more. We expected SO2, we expected more sulfur to come out of the ansatite, especially with AB being so rich in iron sulfides. And so one theory we have is that maybe because it's being housed in more refractory material, and it's hard to get that sulfur out of there. Oh, sorry. Thanks.
Sorry, we're really
I
running
can
out
go
of
on
time.
forever. Yeah.
Yeah. So I'm sorry for the other questions, but please find
Yeah,
in
please.
the break. Let's give him another round of applause. So our final speaker before the flash talk session, I should say, is Chase Alvarado Anderson from Stanford. And he will talk about redox architectures and volatile pathways, linking accretion, core formation, and habitability. So basically wrapping up everything we're talking about. So give it away.
Hi, y'all. I'm Chase. I am a third-year PhD student at Stanford working with Laura Schaefer. Sorry for being late. Yeah, so I want to start a little bit with kind of a general overview, thinking about, as we all know, that habitability is kind of going to be an aggregate of several different factors where we need to know about a planet's thermal, magnetic, surface, orbital, and atmospheric states, as well as kind of the properties of the star. And so I specifically look at the thermal and the atmospheric states. And within these, some of the biggest unknowns that we have kind of surround the redox state, which would tell us a little bit more about what gases we would have. And so kind of using modeling, we can kind of link together the chemistry of the disk to the core, eventually gas, and potentially climate. So kind of a short overview as well. One of the most studied systems that we've been looking at recently is TRAPPIST. A lot of people are fighting for observing time on this, but it's a compact analog of the inner solar system where we see multiple rocky planets that are forming in the same disk. And yeah, it's a great way to kind of think about how planets that have similar mass to Earth would have formed, with 3 of them sitting in its habitable zone. And so some of the big questions that I'm looking at in my study are, 1, how do radiovolatile gradients and M-dwarf disks translate into core mount redox states? 2, what controls the partitioning of volatiles during giant impacts in magma ocean equilibration? And how does embryo mass set the initial volatile budget of these rocky planets? And kind of looking into these things would kind of help us link the physical and the chemical evolution as these planets. And so moving into my model framework, so I have a suite of in-body simulations that I pair with a geochemical model where I can track the mass accretion, so I can look at collisional fragmentation as well as just kind of what's happening with these planetesimals and these embryos throughout time, and then pairing this with solving metal silicate equilibration for each of these impact steps. And so kind of looking at this metal silicate equilibration, kind of just thinking about how these volatiles are partitioning between the mantle and the core and also the atmosphere. And so thinking about these things kind of helps us to learn about the reservoir abundances. What is the abundance of these different volatiles going to be among those reservoirs, and what the redox state and physical properties are going to be of these embryos towards the end of that giant impact phase. And so we had a great keynote yesterday that talked a little bit about this, but in our inner solar system, we kind of see that the mantle iron oxide correlates with the fraction in the metallic core, as well as that kind of fitting this redox gradient in the disk to what we see in the mantle and the core is pretty similar. And yeah, I think kind of thinking about one of the similar studies that looked a little more at Earth and how metal silicate equilibration factored into this could kind of tell us how these initial redox gradients in these disks could potentially kind of change what we're seeing in these partitioning pathways. And so kind of looking a little bit closer into that late impact phase, a lot of people have kind of touched into this, but going from the dust and the grains to the planetesimals to the embryos and finally to our differentiated planet, we end up seeing this bumper car-like phase where we are seeing a lot of heat and energy transferred, and sometimes even a lot of the different embryos being blown off. And so with that, we're seeing melting of the mantle, which is going to induce this magma ocean phase and drive oxidation state evolution. And so that's important as well to kind of think about what types of abundances we're going to have when we move into that outgassing phase. And so a little closer into my model, I'm tracking specifically how these different volatiles are shuffling and thinking about how changes in these experimental partition coefficients are going to tell us where they prefer to be. And so here's one of the important reactions that we're looking at, where we're seeing iron both oxidizing and reducing at these high pressure reactions. And so moving a little bit into my results. So I just want to point out here, the E's stand for like the different analogs in this TRAPPIST system, where we end up seeing that mass is the dominant control for mantle oxidation state. And so here would be like the TRAPPIST 1E analog, where we can see that it also ends up being the most oxidized. And so this mantle oxidation also responds to changes in whatever we set for the metal silicate equilibration pressure. And mass, which is what we're looking at now, as well as the disk gradients and equilibration pressure are going to set that volatile inventory that we end up having. And so across all of our simulations, we kind of see a similar trend where there's a strong mass dependence, and these larger planets are going to end up being the most oxidized. And so redox is not only just an outcome of the disk chemistry, but also of accretion and the physical processes that we have. And kind of thinking about distance and how semi-major axis plays into that, there isn't really a clear monotonic trend. That may change depending on the type of gradient that we set in the planetesimal disk. But yeah, for what we have here, it does not dominate over the mass. And so kind of moving into one of the specific planets I was looking at this 1E planet, and we can see that the CMF was dynamic and it converged, and it kind of would set the stage for what we have available in that reservoir in the mantle that would end up being outgassed. And we see these large swings, these dips and these troughs that are gonna kind of reflect that metal delivery and equilibration. So what volatile content is being delivered throughout that time, and we kind of see it kind of smooth out towards the end. And then looking also kind of at this physical evolution, we have this mass distribution here. Oh, wait. Oh, yeah, sorry. Just generally that accretion history can reshape the CMF as well as kind of the bulk composition that we're going to end up seeing. And so thinking about the geochemical evolution of these, here we can see that this nitrogen is going to sequester largely in the core. We have some partial partitioning between some of the other volatiles, which could mean that there would be a lot less left available for the atmosphere, and that these reservoirs do seem to be impact history dependent. And so over here, just thinking about this step like mantle growth, these jumps and dips that we see are going to be tied to these major impact delivery episodes that we have in the in-body simulations. And so kind of moving into this was all pretty preliminary, but I think what we were seeing was pretty clear that mass does set a lot of the redox, and that would kind of give us a clear indication of what we're going to have available for some of the further steps. And so yeah, mass was what we saw dominating, with the larger planets being a lot more oxidized, as well as this mantle oxidation state changing with our large impacts, and there being a crucial dependence on what we set our metal silicate equilibration to be. And yeah, that it's not just a property of the disk, but also of those geochemical processes that we're seeing, such as the magma ocean episodes and the large impacts, which could also kind of resonate through some of the further things, such as the crustal and atmospheric composition, the surface water retention, and the thermal evolution. I'll stop there.
Thank you for staying at 10. Questions? Let's start over there.
Cool, thank you. This is really interesting. Andy Buchan, University of Warwick. I was just wondering, like, how well does this apply to the solar system? I'm thinking in particular for like this larger planets being more oxidized. Is Mars potentially like an issue there? Or is that are there other things going on?
Right. So yeah, kind of thinking about that disk gradient. So yeah, Mars is going to be more oxidized, and Mercury is more reduced, like you were getting at. But that's kind of the next thing that I'm doing, is applying this specific model to the solar system to see if that kind of holds with the trend that we saw for Trappist.
Cool. Thank you.
Question here in the front.
Hi, Matt Roach, University of Bristol. I was just wondering, how are you setting the pressures of metal silicate equilibration?
Yeah, so whenever we're basically going through and we're equilibrating the impactors by themselves, because it at first kind of proved like difficult to kind of do the full body equilibration, and then allowing that to equilibrate as well with the impactor in the body. But we're kind of using the core mantle boundary and setting that around like 0.5 for now, but seeing that the higher that we set that, the more oxidized we're going to end up seeing.
And do you consider the effects of rotation of the bodies at all?
No, not yet.
I saw one hand over there.
Hi, Hannah Sanderson, University of Oslo. Thanks again for a great talk. This kind of follows on with Matt's question. Are you considering any kind of secondary processes in the magma oceans that could then lead to evolution of redox state, like iron disproportionation or iron sulfide exsolution?
Sorry, what was the second part of that?
Are you considering any like secondary processes in the magma ocean after this accretion that could also influence redox state? So like iron disproportionation or iron sulfide exsolution?
Not currently. I think that the biggest things that I'm going to look to change is probably looking at like CMF distribution, because right now I'm kind of just setting that constant. But I think looking at maybe like a linear or a step wise profile on that would probably be one of the biggest changes. But as far as the magma ocean, no, we're not including anything else with that.
Thanks.
think with that, we should close the session. So let's give another round of applause for Chase. So before everyone runs off to coffee, we have another flash talk session now. I don't know, am I supposed to chair that too? Okay. Yes. Yeah. Okay. And I don't have to keep time. Obviously, this will.
While we wait, so also just a quick announcement after the next session, we will have the conference photo, so all be nice, look nice and fresh. We will do it right outside here. So after the next session, if you just go outside here, you go out there and come back to the right, and then there's some staircases, and there's 2 levels. And what we will do is we will stand on the stairs at the on the ground floor, and actually on these bridges sort of which cross the hall essentially. So afterwards, please don't also run away immediately to lunch. We will have the conference photo first outside of the next session. Thank you.
Do you have one? Do you have one? No, okay, let me get this one.
Oh, this is tomorrow's.
So
Now?
those ones are for now, and then the other one.
Okay. So if the people on this list could make it to form an orderly queue in numerical order. And then just to say that we also have some more flash talks tomorrow, excitingly, because people have been very good and submitted some more flash talks. So these will be the people that we'll hear from tomorrow instead. Show you with the timer.
Yeah. Okay. You have 1 minute.
So yeah, you have 1 minute. And oh, and also one more reminder of the poster competition. And there's also a link to it in the Discord. So go ahead and also make sure that you give yourself an excuse to walk around and look at all the posters before you choose your favorite. So yeah.
Okay, good morning, everyone. I'm Li Haolin, PhD student from Peking University. So in our solar system, we can observe some strong reflection signals from from Earth's ocean or Tasmanian Lake at some special reflection angle. And so this kind of, we call this the gleaned effect. So this kind of gleaned is a strong evidence for oceans or lakes. And we are trying to find these gleaned signals from hot exoplanet. So it's a strong evidence for magma ocean. And if you are interested in our series, please come to our poster. It's just around the corner. Thank you.
Hello everyone, I'm Karen. I'm part of Tim's group here at the Kaptein Institute in Groningen. And I'm presenting my work on the Super-Earth Gliese 486b, which was already mentioned in the first keynote on Monday. It's a really interesting exoplanet that was already observed with James Webb, both its transit and its secondary eclipse in low resolution spectroscopy, as you can see here. And what I did is I used AGNI, a radiative convective model, to model a large grid of surfaces and atmospheres to see if any atmosphere is consistent with James Webb data. And what I found is that steam atmospheres fit the data better than any bare rock surface model, especially if you add this trace of ozone, which you can see here at around 10 micron. However, I also see a large degeneracy between surfaces and atmospheres for this planet, which is why I also look at heat transport and I simulate next observations into Mary bands of James Webb. So if you are intrigued, please have a look at my poster, which is by the Greenery. Thank you.
Hola, my name is Juan Serranoel. I'm a PhD student from Argentina. So as you know, transiting exoplanets around M-dwarfs are prime targets not only for detection, but also for atmospheric studies. And the precise characterization of these targets plays a key role to constrain compositions and to get better atmospheric retrievals. So we revisited 2 transiting planets around M dwarfs with new photometry from TESS and radial velocities from Spiru spectropolarimeter in Hawaii. And the 2 targets are very interesting for atmospheric studies. One is a hot Neptune desert planet and a mini Neptune rich in volatiles. So leveraging the parametric capabilities of Spiru, we were able to study and model the stellar activity in the RVs and compare different models with different components for the stellar activity. And yeah, we were able to improve the precision for both targets in the mass and radius by more than 50% in some cases. And if you want to see more details, my poster is right near the entrance. Thank you.
Hey everyone, this is Tansu Daylan, Assistant Professor of Physics at the Department of Physics and McDonald Center for the Space Sciences. So in this work with my postdoc, we looked at a situation where you have dark matter elastically scattering and sinking to the center of the Earth and heating it from inside out, and the observational consequences that would have on the equation of state of the core. The title is in the form of a question, which is suggestive of an issue here. The actual answer is pretty complicated. Happy to chat over the poster. And in a follow-up paper, actually, more recent paper that went to the archive in the second slide. Can I? Yeah. This is with a different postdoc, Sifan Lin at WashU. We basically conducted a JWST archival survey for thermal excess from planets, small planets, and we find that there are several exoplanets that are indicative of thermal excess anomalies that we cannot explain with known sources of heating, not necessarily restricted to dark matter, but we consider all kinds of heating. Thanks.
Hi, everyone. My poster is all about the rocky exoplanet LHS 344b, which has been previously characterized using Spitzer, and it's an excellent target for thermal emission studies. And now we've looked at this planet using JWST. We detect its eclipse at 40 sigma, which is really nice and gives us the opportunity to study its surface and the atmosphere if it has any. We basically find that we are able to rule out granitoid surfaces. We are consistent with a range of other surface compositions like old space-weathered powdered surfaces. And we are also able to rule out many kinds of atmospheres. In particular, we're able to rule out CO2-dominated atmospheres down to 100 millibars. And SO2-dominated atmospheres down to 10 microbars. If you find it interesting, my name is Sebastian Sieber and my poster is straight and left. If you don't find it interesting, my name is still the same, but you don't have to find it.
Hi, everyone. I'm Bruno Gust. I'm a final year PhD student at the Technical University of Denmark. And I have a poster presenting some of the work that I did with Robin Wordsworth at Harvard. And so basically the idea was that we investigated how on tightly locked rocky planets around M dwarfs, atmospheric collapse and impacts can work together to generate secondary atmospheres. And if that sounds absolutely insane, let me convince you, come to my poster. It's right over there in front of Sebastian's, who just talked. And yeah, that's it. Thank you.
Hi, I'm Alex. I'm a postdoc from UCL, and I'm actually more of a star person. I've managed to infiltrate your community very easily, so maybe figure out your security detail a little bit more. But actually, so as we saw from particularly a lot of talks on the first day, the rocky planets have a low superficial noise, and we'd really benefit if we were able to return to these systems and visit them quite a lot. But unfortunately, the star, or fortunately, if you like stars, the star can be a bit of a barrier to this, as a lot of these smaller, later type stars are quite active. And this activity is modulated on a number of different variability timescales that are probably unique to every star. So I've kind of taken the opportunity to use this poster to initiate some discussions of various methods we could use to mitigate and model this so that actually we could learn about both the planet and the star at the same time if we do it right. If we do it wrong, then I guess we get both wrong and we hopefully still have a good time. So yeah, my poster's somewhere like through that wall, but like don't go through the wall. Go around. Thank you.
Is this someone's poster? Is this person here? Going once, going twice. Go see their poster anyway. Is this your? This is also not yours. Oh, right, it's the same person. There we go.
That's mine. My name is Mei Wu. I'm a third-year PhD student. I'm in Freie Universität Berlin, and I work with Lena Nowak. We are currently building a 1D interior model on a rocky planet accretion process. So we start from nothing into the magma ocean stage. We consider both the planetesimal accretion and the pebble accretion rate. And we are looking at the temperature profile, the physical property, the magma ocean, and the core formation. So if any of this topic sounds interesting to you, or the atmosphere couple, which is we're currently doing, if it sounds interesting to you, come talk to me. My poster is at 85. It's green looking and all the way by the end of the hall. And if you don't find me in front of my poster, come fetch me anywhere.
Hi everyone, I'm Spandan and I'm a postdoc at the Paris Institute of Planetary Science. I started off as an observer more on the high resolution side using ground-based spectrographs, but I'm now also a modeler for atmospheres of magma ocean. My initial project was working on more on the mineral, the rocky kinds of atmospheres, and if we could detect them using the current ground-based spectrographs. So depending on the oxidation state of the mantle, depending on the iron boosted buffer, the atmospheres can be very different. My interest was on if these can be detected and can be differentiated from each other. So if you want to know the answers or about the techniques that we use, please come find me near poster number 28. Thanks.
Hello, my name is Gunnar van Lovre from the University of Vienna. I study upper atmospheres of rocky planets. Here we see a plot showing the distance from the star compared to the stellar mass. And I try to find where can we have planets that are more or less likely to have atmospheres. And I tried it for a bunch of different planets, in this case with different masses, and compare that to planned observations. As we can see, my results are very depressing, sad emoji. However, there are some silver linings, some caveats to take into account that might still change the outcome and be a bit more optimistic than this. But to know about that, you'll have to come and talk to me at poster 41 through the door on the other side of the little wall of posters. Thank you.
Hey, good morning. I'm Kai Wohlfahrt from the Technical University of Dortmund, and I'm particularly interested in modeling thermal emission of airless planetary bodies. And I revisited all the quantities. It boils down to a heat balance equation. I'm interested in the bolometric emissivity, the bolometric albedo, and all the roughness effects. And I revisited everything for the moon and modeled it and fitted it, and for Mercury, and now everything will be transferred to LHS 3844b. For everybody interested in this stuff, please check out poster number 50, right behind the corner on the aisle over there. Thank you.
Hi everyone, I'm Saumil Kelkar, a PhD student at Captain here locally, and I study habitability of terrestrial planets. The habitable zone is classically defined as this region around the host star where conditions are suitable for liquid water to exist on the surface. But this definition is extremely biased by our understanding of Earth and its composition and how life evolved on Earth and now thrives. But as you can see on this plot here on the right, this classical habitable zone is grossly insufficient to accurately characterize the habitability of a wide range of exoplanets, which are non-Earth-like and which have very different properties. So this warrants an extension to the definition of this habitable zone. And so as a first step, We estimate the habitable zone limits using different models just to check if the current framework is robust enough across these different models. And well, the short answer is no. So we propose a new framework to estimate these boundaries. And if you want to know more about it, come check out my poster number 3. It's opposite to the store. It's very green and hard to miss.
Hi everyone, I'm Philip. I'm a postdoc at Freie Universität Berlin, and we want to investigate how sort of atmospheres which may exist on planets today sort of evolved over time. Because a planet's atmosphere is the result of billions of years of evolution, and there's lots of feedback processes going on between interior atmosphere, inside the atmosphere. So what we investigated is starting from very diverse magma atmospheres, which may set the first stage of your planet evolution, and evolve it over time to its current day, and see what types of atmosphere you can get out of that, and what types of, maybe some of these may be habitable. And if you want to learn more, come to my poster, sort of close-ish to the coffee area in the 70s, and you can see how diverse atmospheres you can get, or how similar atmospheres we can get. Thank you.
Hi, my name is Bram de Winter. I'm a PhD student. When magma oceans crystallize, every mineral melt phase will have a distinct isotope, stable isotope fractionation factor. We calculated in the poster, the data on the poster, we calculated a couple of these, including the silicon and magnesium bridgemanite melt factors. And as anyone who basically has seen any isotope ratios, they're quite big. So if you want to know more about how these influence, for instance, if we could explain the Earth-chondrite differences, or how the magma ocean crystallizes and what we can tell from there, come and visit my poster. It's on the upper side, on that side. Thank you so much.
Are you tired of your retrieval framework ignoring atmospheric thickness in eclipse observations? Fix this today by changing just one line of code. Altitude profile required, but sold separately. Jokes aside, I'm Giacomo Gallina, a first-year PhD here in Groningen. My poster is somewhere over there, so if you want to know more, come and talk to me.
I think that was everything for today. So thank you very much. And we now have a little coffee break. So see you back here at 11:15.
Okay, I'm excited to welcome you back to the next session. I hope you're all refreshed and rejuvenated after a short coffee break. I'm very pleased to welcome the next speaker, who is Charles Edward Bucari, who's going to talk to you about planetary interiors. Thank you.
Good morning, everyone. I'm Charles Edward Bucari. I'm an assistant professor at the Department of Physics and Astronomy at York University. I'm going to talk about planetary interiors. It's a real pleasure to be here. To be honest with you, it's my first Rocky World Conference, and I can't believe that I've waited so long to attend this conference. So thank you very much to the organizer, everyone who organized the meeting, for the invitation. It's really an honor to talk about planetary interiors that I like a lot. So today I'm gonna discuss a few concepts that is currently used in the exoplanetary community to infer the interior structure of exoplanet, of rocky world, and concepts that we learn from the solar system. You will see those concepts that we will discuss are actually relatively simple, and I hope you will be able to find a connection between the work that you are currently doing and those concepts that we'll be discussing. I will also probably exaggerate a lot those concepts to make my point as clear as possible. But hopefully this will make sense and this will not be too approximated. Before we move to those processes, I would like to talk a little bit about the data. Because we will see those concepts, the idea is to combine those concepts in a creative manner. And in science, it's good to be a bit crazy sometimes. But if you want to build testable hypotheses, we have to look at the data. So I'm going to distinguish right now two different eras of the data that we have for research in exoplanetary sciences. And the first era would be the era of mass and radius measurements. So as you all know, this started with the first observation and of an exoplanet. With the mass and radius measurement, we can get the bulk density, and with equation of states, we can infer whether the planet is mostly a gas giant or a rocky planet or a super Mercury. We then pushed this kind of reasoning to its limit to maybe infer, well, what is the size of the volatile atmosphere? What is the size of the rocky mantle? What is the size of the core? And it has been shown very early on that this is a highly degenerated problem. So we need to find ways to better constrain this problem. So compositional link between planet and the host star has been used as a constraint, but still it's very difficult to tightly constrain the interior of rocky planets. So as you all know, people then got really excited about the second era of exoplanetary research, where now we have potentially access to the surface or the atmosphere of those rocky worlds. So now we add another kind of data set to the problem. So we have mass, radius measurement, and maybe if we are really hopeful, the composition of the atmosphere. So it's like now the game has changed a little bit. So my talk today will discuss planetary interiors in the light of these data sets and what concept can we use to use as best as we can all those data. You also know that the community didn't wait for GWST to study atmosphere and interior interactions, so a lot of work has been done to predict and anticipate what kind of science we can do once we will have access to constraints on the surface. So I'm going to talk, of course, a bit about this, but you will see I will focus a lot about what is done recently and what we might do, what we might be able to do in the future. So this is a way to restrict a little bit more of the concept that we will discuss. Again, I'm going to use concept or describe concept in the light of the data that we have. So how can we link the interior to the surface of planets? And I'm going to focus on the deepest part of rocky planets. I know a lot of you are working on coupling the atmosphere and the interior. I'm going to focus really on the deepest parts of rocky planets. So this is a very simple picture of the problem. We're going to have maybe atmospheres, maybe a bare rock surface, and we want to link the surface with the interior. So what can we do? So imagine a glass of tequila. I'm sorry I had to steal this analogy that is really nice, so I thank the owner of that joke. But this is a really good analogy for what I'm going to discuss in this presentation. So we have the grenadine at the bottom. And you know, if you drink that glass very gently, you're going to taste only the orange juice. So this is a way to introduce the concept of layering. We're going to talk a lot about layering today. And as you know, in the very first studies that were used to infer the interior structure of planets, this is a kind of layering that we invoked for explaining the structure of planets. Atmosphere, rocky mantle, iron core. But now that we're introducing more and more geological processes, this is a kind of pictures that we start to see in the literature of exoplanets. Because this is what we see on Earth, on our rocky planet in the solar system. We have an upper mantle, a lower mantle, basal magma ocean. For those who know me, I like basal magma ocean a lot. Liquid core, solid core. So we have all these different layers now. So I'm going to discuss in the first part of this talk, how can we form those layer concepts that we need to understand how we can form those layers. Why those layers are really important? Because from the compositional perspective, they will behave very differently. And again, the idea is to connect the interior to the surface, and the surface, what we can hope, is to have data on the composition. So we need to find a way to connect the interior to more detailed aspect of the composition. And the two concepts that we're going to discuss are the concept of storage capacity. What can we put inside those layers? One thing. The other concept that we'll be discussing is the concept of chemical equilibrium, because those layers can interact, and we need to account to some extent to this chemical equilibrium if you want to make your way all the way from maybe the deepest part of the planet all the way to the surface. Finally, in the third part, so in the second part, we're going to talk about storage capacity, partitioning coefficient. If we have the time, we're going to talk a little bit about phase assemblage. In the last part, we're going to talk about the dynamics. Those layers are not necessarily static layers. You know, in Earth sciences, planetary sciences, we know that at least for Earth, there is a lot of convection going on there, and this might promote maybe chemical equilibration between those layers. Maybe this can inhibit chemical exchange. So we want to be able to capture those processes, or at least to predict what would be the outcome of these processes. So this will be the third part of this talk. So let's start with the first part, the structure. So what I mean by structure is layering. To be honest with you, I don't like the word layers because I find it really confusing from a dynamics point of view, because we can create layers, we can destroy layers, it could be time dependent anyway. But I'm going to still use the word layers in this presentation. So if you look at the literature of Earth sciences, there is an important concept that is a concept of, especially in geochemistry, the concept of hidden reservoir, hidden geochemical reservoir. The fact that maybe what we see at the surface is not exactly representative of the bulk interior. So you can keep in mind in a very simple way, for the Earth, we have access to meteorites that can constrain maybe the bulk of the rocky planets, and we have access to the surface of the planet. So if you, with the meteoric records, you know that you have tequila, grenadine, and orange juice, but at the surface of the planet, you see only orange juice, you have a good rationale to say, oh, my grenadine is missing here. So this motivated a lot of research in geodynamics to maybe find a way to explain some kind of layering. So this is relatively odd in the literature of geodynamics, and here I'm showing you an example, a specific kind of a double layer convection, where you have those two layers convect, and you have a stagnant lead here at the top. We're going to see today a few ways to generate this kind of layerings. This one is really specific, where those two layers actually convect. So you see some interactions between those two layers. There's an entire zoo of different regimes where maybe this one is stably stratified and would convect. We don't have the time to cover all of this, but you can keep that in mind. So there are many ways to create this layering: compositional effect, pressure effect, temperature effect. For this presentation, I'm going to talk only about compositional effect and temperature effect, because I do not have the time to cover everything. From a compositional perspective, actually, it's fairly easy to understand. The idea that you're going to have a layering if the compositional buoyancy or chemical buoyancy is larger than thermal buoyancy. So this is a cartoon of some kind of experimental setup were designed in the 80s to explore this kind of physics. So the chemical buoyancy here would be delta rho. And the way they can adjust this chemical buoyancy in this fluid dynamics experiment is by varying the ratio of glycerin in the system versus the ratio of water. So this is the chemical buoyancy. And then you will impose some temperature gradient across this layer to generate thermal convection. That delta T here would be what would drive thermal convection. So this would be the thermal buoyancy. It has been shown that if what we call the dimensionless buoyancy number is larger than 1, you will generate layers. Same thing, from a fluid dynamics perspective, you have entire regimes where it's slightly lower than 1, slightly larger than 1. But at first order, this is what you want to have in mind. Why is this important? Because thermal expansivity for silicate rocks, so here if we look at silicate rocks, is relatively small. It's quite small. It goes to 10 to the power -4, -5. So even though if you have like thousands of Kelvin as a delta T to drive convection, you do not need much delta rho for the composition to promote a layering. So if you do this exercise for silicate rocks, just 6% of Fe, FeO would be able to stabilize a layer. So it's really easy somehow to get into those regimes. Now let's move to the second aspect, that is viscosity. I didn't mention this when I started because viscosity can depend on composition, temperature, pressure, but let's look at just viscosity. This picture, I like this picture a lot because it's a good illustration of why layers might not be really relevant. So this is a model that Maxim is probably here, proposed a few years ago to challenge a little bit this idea of layerings and how we can build models that might look like double two-layer convection at the top of the planet, but actually the dynamics inside is very different from two layers convection. So you have here, so this is the surface of the mantle, this is the core mantle boundary, and you can see here the compositional field, and you have those giant blobs here that are enriched in silica. It has been shown that silica will increase the viscosity of silicate rocks, so those layers will be very, very viscous. It won't be possible to mix those layers with the other components, so you will isolate those reservoirs, and so what you will see at the surface will not reflect what you have here. So if I think this in terms of tequila, this is orange juice here, and the grenadine is all there. Okay? So some kind of way to actually hide stuff in the mantle. Now we're gonna move to, to the last aspect of layering that I would like to discuss today. That is the role of temperature. And I'm gonna take the example of the structure of planetary cores. So we know that planetary cores, you have some of them that might be fully liquid, others would be fully solid, and maybe some of them would be partially solidified. What do you need? What kind of information do you need to predict this state? Not much. The core temperature, you need to find a way to predict the core temperature, the slope of the core temperature, and you need to know the melting temperature of the material. So if you're interested in the core, that's going to be the melting temperature of iron. And you want to compare the slope of those two. So here I'm going to show you the temporal evolution of the system. If you start with fully liquid here, and the two slopes are such that the core temperature will intersect the melting temperature at the bottom of the system, you will start to crystallize from the bottom. And as the system cools down, the size of the solid layer will increase, and little by little, the thickness of the solid layer will grow at the expense of the liquid layer. This is a canonical model. I really invite you to look at these papers that summarize different ways of crystallizing planetary cores. And maybe this is something that could be good to have in mind when we want to predict the thermal evolution of rocky planets, where we might not know the slopes, what's the difference between those two slopes. And you can create really exotic kind of layering. this concept here that is discussed a lot in the context of core solidification would still can still be applied to the solidification of the mantle, when the mantle might be partially molten. So when we talk about lava world and stuff like that, maybe this kind of thing could be important. Okay, so we are done with this kind of layering. Now we're gonna discuss quickly from a compositional perspective why this layering could be important. The idea here is to discuss what can we stuff in those layers. And there are few concepts that we want to discuss. Again, I hope there will be nothing really difficult. It's probably things that you know already, but again, I think in the future, we want to combine all the different contexts in a really creative way, and there is still a lot we can do with those. So I would like to talk about the concept of storage capacity. So how much of an element we can put in a given layer. In this part, I'm gonna use water to illustrate this concept, but you can actually apply this concept to any element that you like. But I'm gonna use water here. So when we talk about water, and let's say we're gonna start with solid rocks, how much water we can put in those solid rocks. So there are some rocks that we call anogenous minerals. So they do not incorporate water in their crystal structure. It has been shown that you can put a few weight % of water in those anogenous minerals. Few weight % is not a lot, but if you integrate this on the volume of a silicate mantle, it could be a few Earth oceans, if you take the size of the Earth, for instance. So it's still a lot. If you move to now hydrous minerals, now those minerals actually incorporate H2O, or actually OH, in their crystal structure. So when you write the chemical formula of those crystals, you will see OH will appear. You can put a bit more of water, maybe one order of magnitude more water in those minerals. Now, if you move to actual silicate melt, it has been discussed, in the past 2 days, that you can put a lot of water. If you reach actually the miscibility, you pass the miscibility limit of water between silicate and melt, you can actually almost put as much water as you want in the silicate melt. So potentially it could be a big reservoir for water. Just one quick thing. You might wonder, well, how do I know if I have hydrous mineral, non-hydrous minerals? You want to look at the stability field of those minerals. So this is something that has been studied a lot in earth sciences in the context of dehydratation of slabs and stuff like that. So this is not representative of the literature of this kind of problem, but it's just to illustrate if you need to have a look at those data. You're gonna see a phase diagram like this, where you have pressure, temperature, and you want to determine in which region of the pressure and temperature diagram you are to maybe identify where you can find those hydrous minerals that can store a lot of water, or maybe if you are in the molten region where you have melt that will store even more water. Now I would like to contrast the concept of water storage or storage capacity with partitioning coefficients, because I find it actually in the literature sometimes extremely confusing when we use, in the extreme case, storage capacity as a way to predict the amount of water, in that case, that could be in that reservoir. It's not because the water capacity is large that you're gonna necessarily have a lot of water in there. In the first place, you need to bring this water. So now the question moves towards more the accretion of the planet, how much water you can bring to the system. Second, if that layer is in equilibrium with other layers, those two will interact. And so maybe now it's more the chemical partitioning between the reservoirs that is more important than the actual storage capacity of that reservoir. So it's also a bit confusing because we use different words to describe this process. And you hear a lot the term solubility limits, solubility laws, saturation limits, all those things. So here, for instance, I would like to contrast maybe the solubility limit, that the way I use it is really the storage capacity, with solubility laws. When we talk about solubility laws, now we talk about two phases that are in equilibrium. So solubility laws would be the equilibrium between a melt and a gas phase, okay? And you can then extend this concept to other kind of equilibrium between two liquids. So this has been studied a lot for the context of deeper sciences, for instance, equilibrium between metal and silicates. So here, this is an example, for instance, of the partitioning coefficient of water between metal and silicates at high pressure. So here I should have put the pressure, it's really important here, 135 GPa. So in these papers, they showed that water seems to be siderophile at high pressure, so we'd like to go into the metallic phase, whereas at low pressure, we know it's actually more lithophile. You want to then have access to the equilibrium between melt and crystals, so this is another kind of family of partitioning coefficients. And if you want to be actually exhaustive, you can also consider equilibrium between solids. For the case of water, it's maybe not relevant, but just to let you know that all of this is part of the story. So just to illustrate how powerful those concepts are, this is a paper that I really like that actually exemplified in a very elegant way why we should care about those layers. So it has been shown that if you assume that the structure of the planet is just a solid core with a solid mantle, the only part of the planet where you can actually put a lot of water would be the volatile atmosphere. But then if you invoke molten layers, you can now store a lot of this water in the interior. And so for a fixed density and planetary mass, you will observe very different size of the planets. So in these papers, I showed that you can change the radius of the planet by maybe 10, 15%, I think. So just one way to illustrate, when we combine all those concepts, this is what we can get. Something that I would like to now discuss really rapidly, and this is probably a question that we might not be able to answer, at least on the short term, is planetary interior chemistry universal? Meaning, can I use safely all those partitioning coefficient, phase stability data that has been done on maybe Earth-like composition? Can I apply this directly to other planets? And actually, it's a tricky question because sometimes, yes, it works. So I just pick here some example. Again, the literature is really large about this. But one example here showed that, well, if you dope the planet in carbon, you might think that, oh, the chemistry will totally change. You will find like weird carbon phases like silicon carbides, weird stuff. Actually not. All the carbon will be expressed at the graphite layer, and the rest of the mineralogy would kind of look like what we are in the solar system. In other cases, it's qualitatively the same, but quantitatively a bit different. So you want to be careful and maybe investigate, explore, or vary a little bit quantitatively those values to maybe anticipate quantitatively what would be the role of those variations. And in some cases, if you maybe talk to the earth science community, they will be very extreme. They will be like, no, you cannot use this in other pressure, temperature, or chemical environments because those values are extremely sensitive to pressure. So for instance, metal silicate partitioning experiments, they showed that those coefficients are really sensitive to pressure, and this is how we can actually predict at what pressure the silicates equilibrated with the core. So I think we should keep an eye open on all experiments that will be done in the future that can maybe try to sample different PTC space that could be relevant for exoplanets. So now I'm going to move to the last part, and I'm going to talk maybe a bit more about my research, where I try to couple geodynamics, fluid dynamics with chemistry, because I think in the future, if the constraint that we have on the surface of the planet are the chemistry, we need to incorporate chemistry to some extent in those dynamics models. This will be also a way to go beyond the static description of rocky planetary interiors, because we know the structure evolves, and we should be able to distinguish maybe old systems from young systems. I will distinguish two different kinds of dynamics here. What I'm going to call surface geodynamics from global planetary interior dynamics. A lot of work has been done on the surface geodynamics for good reasons, because the surface lies exactly at the intersection between the atmosphere and the interior. And as you know, there is this really important question about the regime of the geodynamics that we should be in. Is it plate tectonics, stagnant lead? There is a new regime that has been proposed recently. This will affect tremendously the chemical exchange between the interior and the exterior, so thermal exchange. A lot of work has been done on this, so I will actually not review all the literature of this. I will focus on the global interior dynamics today, and to maybe illustrate what we can do now with the computational power that we have, and how we can maybe better include or combine chemistry and fluid mechanics. So this is something that is sometimes called geochemical geodynamics. Paul Tackley, that is probably here in the room, was one of the pioneers in doing this kind of modeling. And I think that is something that on the long term will be really important for exoplanetary science if we want, again, to say something about the composition of the surface based on the dynamics in the interior. Here I'm going to focus on a very specific kind of exoplanets that are lava worlds. So those are really hot, as you know, rocky exoplanets. And we believe, well, at first order, they should be tidally locked. So we're going to have a day side where the surface temperature is expected to be hot. And we should have here shallow magma ocean at least, and we have a night side that's expected to be cold. This temperature difference at the surface will drive global circulation. And we have here this magma ocean that is in contact with a solid. So we expect here to have chemical interactions between the magma ocean and the solid. And this is something that has not been explored so far. So the same way as a lot of us here are coupling the magma ocean in the atmosphere, I want to do the same thing here, but to couple the magma ocean with the solid interior. And to do this, I'm going to use a code that I've been developing since my PhD that actually implements the physics of multiphase flow, the theory of multiphase flow, but the idea is to extend or to apply this physics at planetary scale. The power of this approach is that I can now account self-consistently for all those processes that or those concepts that I've introduced. So if we talk about the structure, where do I have a liquid layer? Where do I have a solid layer? I'm going to solve self-consistently the fluid mechanics. And I'm going to track energy transport, and I can self-consistently observe where my liquid is solid, where my liquid is liquid. I do not need to impose anything. I can constrain the chemical composition of the liquid and the composition of the solids based on partitioning coefficients that has been published in the literature. So I can now predict self-consistently of the composition of the magma ocean will evolve, of the composition of the solids will evolve, without having to, again, impose anything. Well, what I impose are the partitioning coefficients. And most importantly, I can solve the time evolution of the system. So this couples two Navier-Stokes equations that would allow me to track the phase separation of the liquid from the solid, as well as thermochemical convection or thermocompositional convection in the planets. So what you will see here is the first model of the solidification of lava planet in 2D. I have published also recently a model, a 2D, the first 2D model of solidification for an Earth magma ocean. And you will see the power of this kind of modeling is to capture the feedback, the complex feedback between chemistry and fluid mechanics. So here I'm going to show you the fluid mechanics of this lava planet. So you have on the left side, the day side. So this is the surface of the planet. This is the core mantle boundary. So this is hot, this is cold. This is the melt fraction field. So when it's fully white, when it's all white, that means that it's fully molten. You will see we're going to cool the lava planet. So it will become more and more solid, so more green. And below here, you have the compositional field. I'm going to track FeO here, because FeO has a strong feedback on the fluid mechanics. It's a dense component, and it's also a fusible component, meaning that when you increase the FeO content, you decrease the melting temperature of the material. So this is the fluid dynamics. So I start fully solid. I have convective motions. You can see some of this global circulation there. So the system starts to crystallize. The crystal fraction increases. And then I'm left with a shallow magma ocean at the end, a mostly solid planet here. And you see here maybe a basal magma ocean here at the bottom of the planet. Look at the structure of this mantle here. This becomes self-consistently stratified because since FeO is incompatible, it would stay in the melt, and so it will increase the density of the material, and then you form this layering. So again, tequila, grenadine, orange juice. So I'm running out of time here, so I'm going to stop here. And thank you very much for your attention.
Brilliant. Thank you for a very nice talk. I can see a big hand up at the back there. Don't mind.
Hi, Thomas Wilson, University of Warwick. Very interesting talk. I was wondering about actually your last point on the your Bambari code and this interior dynamics. What are the kind of timescales that we were looking at of the different convections that you were showing on your last slides?
Yes, excellent questions. So the time scale that I'm looking at here, we are talking about, so let's say you do not, your primordial energy is just residual heat from accretion. We are talking about few hundred of million years. So maybe 100 to 500 million years. Something that I didn't have time to discuss is that in the context of lava exoplanets, maybe tidal heating could delay these early stages. So this is why I believe maybe we could have a chance to observe those lava world in a, maybe not fully molten, but significantly molten state.
Okay. But by 500 million years or a gigayear, this should all have stopped, unless you have this.
Yeah. Yes, unless you can find a way such that you have some kind of resonance and can maintain a high temperature in the lava planets. But yes.
Thanks.
Thank you.
Okay, maybe can the next speaker come and set up? Well, we have one more question at the back over there. Right at the back. And can I remind you to say your name and institute as well?
Mark Braam, University of Bern. Thanks for a great talk. I was wondering what are your initial conditions for the global dynamics models in the first place, and how sensitive is solidification against these initial conditions?
So in these models, the initial conditions are fairly simple, homogeneous in temperature, homogeneous in composition. The point I wanted to make is that we can have fractionation during the evolution of the system. To be honest, I will be less worried about the initial conditions, but more all the other parameters that actually control the evolution. such as the efficiency of solid-liquid fractionation. This is something that is still discussed in the context of the Earth. So yeah, I would be more worried about those parameters than the initial condition.
Okay, let's thank Charles, and just in the interest of time, we're going to move on. So I'm delighted to introduce our next speaker, who is Jaisal Patel, who's going to be talking about lava rain, volatile atmosphere, or something else. Thank you very much.
Pointer. Yeah, here. Hello, everyone. Good morning. I'm Jaishil. I'm a postdoc at DTU Space in Denmark. And today I'm going to tell you a tale of a hot rocky planet, 55 Cancri E, as seen by the James Webb Space Telescope. Despite having been observed extensively throughout the last decade, its nature is still puzzling. We think that it might be raining lava on this planet, or it may have a volatile atmosphere, or maybe something else. So let's find out what JWST has to say about the nature of this planet. But before I begin, I would like to thank all of my collaborators for their contribution to this work. Our paper is already published, so you can scan this QR code to read our paper. Before I tell you the story of 55 Cancri E as seen by JWST, I would like to introduce some of the main characters of these stories. And first, I would like to begin with the method that we use to study 55 Cancri E. We basically use planetary occultations. Occultations happens when a planet goes behind its host star, and using this observation, we can basically measure occultation depth, using which we can estimate the day-side emission from the planet. We can actually measure occultation depth as a function of wavelength, giving us the occultation depth spectrum. In this plot, I'm showing you the model of occultation depth spectrum. Using this, we can estimate the day-side emission spectrum of the planet, and using that, we can find out if the planet has an atmosphere or not, and if it has, then what kind of species this planet has. Okay, so this is what we use to study 55 Cancri E. Now, the main character of our story, the planet 55 Cancri E. It's an 8 Earth mass planet. Radius is about 2 Earth radius. This makes its density about 6.6 gram per cubic centimeters, which is consistent with the rocky composition. And indeed, an internal structure modeling of this planet suggests that the planet indeed has a rocky composition. While it cannot sustain a primordial hydrogen and helium atmosphere, but it can certainly have a secondary heavyweight atmosphere. There are other 4 planets in the system, but this is the only transiting planet in this system. Its orbital period is about 17.7 hours, and that's why it is very close. This figure is actually drawn to scale, so you can see that the planet is actually very close to its host star, and it is also very small compared to its host star. The star is a very bright star with a visual magnitude of about 5.95. It is actually a naked eye star. So it is quite easy to observe this star. And this was also one of the first rocky planets ever discovered. Because of this, the planet was observed extensively throughout last decade with many ground-based and space-based observations. One of the main goals of these observations is to find out whether the planet has an atmosphere or not. Several observations have tried to search for many species in the atmosphere of the planet. There was a claim of some detection, but that was not collaborated afterwards. Essentially, many observations have failed to detect any chemical species in the atmosphere of this planet. So maybe there is no atmosphere on the planet after all. However, Spitzer Space Telescope also observed the planet, and it found a hint of a day-side atmosphere on the planet. So what's going on? Does the planet have an atmosphere or not? Spitzer observed the planet extensively throughout several years. And in this figure, I'm showing you the summary of those observations. Occultation depth as a function of time and transit depth as a function of time. While transit depth is basically consistent throughout several years, occultation depth seems to be varying over several years. This variability in occultation depth is not limited to infrared observation, but it was also observed with Cheops in the optical bandpass. So this is occultation depth with as a function of Cheops visit, and this is a phase co-amplitude as a function of Cheops visit, and you can see that both of them are clearly variable. So when JWST was launched, we were eager to observe the planet with JWST. This is one of the first observations of 55 Cancri E with JWST. I'm showing you the occultation depth spectrum of the planet, and this feature, this seems like a hint of a carbon dioxide or carbon monoxide atmosphere on the planet. So what is going on? Maybe there is an atmosphere on the planet after all. But what about variability? Variability on this planet is still a puzzle. And in the literature, there are several hypotheses to explain variability of this planet. While some of them can explain something, but none of them can explain every aspect of observations. So my PhD supervisor, former PhD supervisor Alexis Brandecker, he proposed a hypothesis suggesting that maybe the planet is not tidally locked, but maybe it is in 3-2 spin orbit resonance. This could be possible because the planet can be gravitationally perturbed by the outer planets in the system. If that is the case, then the planet could be trapped in 3-2 spin orbit resonance. And if that is the case, then we should not see the same face of the planet every time during the occultation, but instead we will see different faces in consecutive observations. In particular, if the planet is indeed 3-2 spin orbit resonance, it would essentially have like two phases, and in consecutive observations, we will see like phase 1, phase 2, phase 1, phase 2 like this. For example, in this video, I'm showing that the arrow will show one of the faces of the planet. Now the arrow is facing towards the observer. Observer direction is downside, transit, and occultation. Now the arrow is pointing away from the observer, and now it will point again towards the observer. So essentially, the planet would have two faces, and these two faces can have very distinct physical properties. And because of these distinct physical properties, it can have very different occultation depths. If that is the case, then this model can naturally explain the variability that was observed in optical and also in infrared. If that is the case, then the hottest point on the planet would not be at the substellar point, but it would be away from that. And the thermal inertia would be provided by the vaporization of rocks. And this rock vapor can condense in the evening, hence the lava rain in the evening of the planet. We obtained time on JWST with NIRCam to observe 4 occultation to test this hypothesis. The idea was that the planet would have two phases, so we wanted to observe 2 occultation with phase 1 and 2 occultation with phase 2. And we wanted to observe all 4 of them within a week, so that because if the planet's surface is changing over a long time scale, we will not see anything. So we wanted to observe all of them within a week. But unfortunately, we could only observe 3 of them within a week. The 4th one was scheduled like 4 months afterwards. Fortunately, there was another program that was observing 55 Cancri during the same time. So we essentially got 5 observations. 4 of them were observed within a week, and the 5th one was observed after like several months. If you observe a planet with NIRCam, you get 2 essentially simultaneous observations, 1 photometric observation at 2.1 micron, and 1 spectroscopic observation between 4 and 5 micron. So now I will show you the results of these observations. What I will show you is the occultation depth as a function of epoch number. And as I said, if the planet is indeed in 3-2 spin orbit resonance, it will have phase 1 and phase 2. Phase 1 is with green and phase 2 is with purple here. So this is what we found. In the orange, I'm showing you the occultation depth at 4.5 micron channel, and in blue, I'm showing the occultation depth at 2.1 micron channel. We were expecting to see similar occultation depth when we see phase 1, so in green, and similar occultation depth in phase 2, so in purple. But you can clearly see that the occultation depth during phase 1 is quite different, especially at 4.5 micron. So maybe the reason for variability is not that the planet is in 3-2 spin orbit resonance, but now we got a variability, and very huge variability. And you can see that this is just 6 days. Within 6 days, the occultation depth at 4.5 micron, for example, changed from about 0 ppm to more than 100 ppm. That's a huge variability. And this is not limited to 4.5 micron channel, but that was also observed in 2.1 micron channel. For example, the occultation depth changed from 50 micron to 0 micron, basically non-detection, within few days, actually. The curious one was also this. So in this observation, we basically observe the similar occultation depth at both 4.5 micron and 2.1 micron. So what's going on here? If we translate this occultation depth in temperature, this is what we can find. The brightness temperature was changing from about 800 kelvins to more than 2000 kelvins just within 6 days. That's a huge change. Now, I told you that we can also get like occultation depth spectrum between 4.5 micron, between 4 and 5 micron. So now I will show you that this 5 panel shows the observations in 5 different observations. Visit number 1, 2, 3, 4, and 5. The black data points are basically our observations, and in the colored line, we tried to fit different models using our atmospheric retrieval framework. We basically tried flatline model, black body model, carbon dioxide and carbon monoxide model, and silicate models. Our Bayesian analysis suggested that only in 2 visits, the atmospheric model was favored, in visit number 1 and visit number 3. In all these other 3 visits, we could not statistically confirm statistically find the hint of an atmosphere. And these are basically the these are basically the pressure and temperature from our atmospheric retrieval analysis. So what's going on? Why are we seeing this variability and huge variability? So we suggested 2 hypotheses that can explain this variability. One of the first hypotheses was that maybe there is an atmosphere on the planet, but it is a transient one. So at some point, there is no atmosphere on the planet at all. And at that point, we are basically observing the hot rocky surface of the planet. But because of outgassing, the planet can outgas some of the atmosphere, and it will create like a thin atmospheric layer. And this thin layer, and if there is a thin layer, then what we are observing is just emission from the surface and the atmosphere. This atmosphere can get lost because of escape processes. So after a while, we can see again the bare rock. So this transient atmosphere can actually explain our observations. However, note that we also have observations at 2.1 micron and 4.5 micron. It is very difficult to explain both of these observations simultaneously. You can see that occultation depths are doing different things at 2.1 micron and at 4.5 micron. The occultation depths are basically not correlated in both channels. Here, the occultation depths increase, while in the first 2 observations, occultation depths decrease between first and second observations. This tells me that maybe the source of this variability is different at 4.5 micron and at 2.1 micron. So we suggested that maybe at 4.5 micron, we are actually seeing what is on the planet. But at 2.1 micron, we are seeing something else. And that could be, for example, a circumstellar dusty torus in the circumstellar environment. This dusty torus can be formed, for example, from volcanism on the planet. Volcanism expels some gases in the atmosphere and some dust. And this dust can afterwards just escape the planet and form a circumstellar inhomogeneous dusty torus. And that is maybe what we are seeing. However, with our observations, it is really hard to distinguish between both of these scenarios. We need basically multiple observations simultaneously at multiple wavelengths. And with that, I thank you for your attention. And
Brilliant. Thank you for a very exciting talk. Are there any questions? Right at the back there. And just remember to say your name and institution.
Hi, Christopher Monin from the University of Montreal. I'm curious as to how robust a potential phase curve observation would be in sort of analyzing the 2 potential or 3 potential causes of the variability. Would that be like a possible JWST cycle observation in the future to perform phase curves?
You mean the Spitzer phase curve are you talking about?
Yeah, because I know there were Spitzer phase curves, but would like JWST phase curves also provide further
Yes, but there are no JWST phase curve as of now.
Okay.
Okay, any more questions? I can see one in the middle there.
Hi, Hi, Johanna Teskey, Carnegie Science. Thanks for your talk. Can you comment on the level of systematic noise in your, this is like a little bit of a question I know you're prepared for. Systematic noise in your data and how that compares to the different options to explain the variability.
Yes, so now I'm showing you the actual light curves, and you can see that especially at 4.5 micron, there's a huge systematics in the data. And we actually don't know the reason for this systematics. We don't know if it is coming from the star or if it is coming from the instrument. To mitigate this, what we did was to simply perform an injection retrieval methods to inflate the uncertainty so that we are sure that we are taking care of this. We did not actually model this, but apart from this, we are still seeing the variability, difference in the occultation depth. So that should be, we are certain that it is there, yeah. But the systematics is issue, yes, right. Thanks.
Okay, brilliant. Thank you for a really nice talk. So I'm absolutely delighted to introduce Mohammed Farhat, who'll be talking about magma ocean waves on lava worlds.
Yeah, down to go forward.
Yeah, very intuitive.
Very intuitive. Thank you. Okay. Hi, everyone. This is Mohammed from UC Berkeley. And in this talk, I'm going to try to summarize my recent work with Eugene Chiang on the fluid dynamics of magma oceans. And I'm going to heavily rely on the excellent talks that we just had on the interiors and 55 Cancri. So to start with the very basics, take any silicate mantle on a rocky world and start heating it up. You start generating melt, and then you transition into a mushy regime, and eventually into a fluid magma ocean, which is gravitationally mobile. And the question that I'm trying to address in this work is, take this lava world, magma ocean bearing world, and subject it to some gravitational stresses from its host star, from a companion planet, or from a satellite. How does this magma ocean respond to this gravitational forcing? And what kind of thermodynamic effects do we expect, especially in terms of observables? And the motivation in this study was that, looking into the literature, I found that this phase transition from an immobile solid to a mobile fluid was basically accounted for by just tuning a knob, which is that of viscosity. So you go from a solid to liquid, and then you just lower the viscosity by orders of magnitude, all the while maintaining the governing system of equations that describes that of the deformation of viscoelastic solids. So what I wanted to do is to account for fluid effects, and the problem with this traditional treatment of solids is that, as you saw, viscosity drops exponentially the moment you start generating melt and increasing the temperature, and so does tidal heating. The amount of heating generated in a viscoelastic solid drops proportional to viscosity, so the moment you generate melt, you shut off tidal heating. But that's not the case for fluids, because fluids have different pathways of dissipating energy that are independent of the lowered viscosity. And so for the rest of this talk, I'm going to hide all the details under the carpet, and I'm just ask you to trust me that we did take this into account using the proper system of equations for fluid dynamics. I'm just going to show some expected results from accounting for this fluid behavior within magma oceans. So to start with, just imagine a lava world, say 55 Cancri, for example, 55 Cancri, where the magma ocean is confined to the day side and a frozen night side, and it's being tidally forced by its host star. And what I'm plotting here is the amount of tidal heating generated within this thin shell of lava over the amount of energy released by the stellar irradiation, which is already intense. As a function of two things: first, the thickness of this oceanic layer, which is on top of the mantle, and second, another model parameter, which is a characteristic time scale of damping the lava flow. So you're generating a flow within this magma ocean by tidal forcing, and then you damp it by some dissipative mechanisms, and there's a characteristic time scale associated with this damping. So what you see is that we have a peak of dissipation of energy release, which allows the surface to be completely dominated by tides rather than stellar irradiation. And so we expect different kind of behavior when we allow for these lava waves. And to understand this peak, it's very simple, basically. You can just imagine shaking any viscous fluid or just trying to move it around. I wish I can use the example of our famous
cocktail now, but it has to be viscous. So she's just shaking a pan of honey at some fixed frequency, just like tidal forcing is periodic, and seeing what happens. If the layer of honey is very, very thin, it would just slide elastically without doing any shear. If it's very, very thick, only a thin layer at the bottom would dissipate energy while the rest of the honey column would sit idle. But for some intermediate thickness in between, the whole column of honey would move coherently, maximizing the amount of energy dissipated in the process. So we expect first that for these ultra-short period planets, when there's a source of tidal forcing, their surfaces are completely dominated by tides when we allow for this fluid behavior of lava. Second, a very important difference between accounting for these planets as low viscosity solids versus fluids is that when subject to a gravitational forcing, say for example, a mode of the gravitational forcing, the lower order mode, L equal M equal 2, the response of the planet is exactly that of the forcing. So there's one-to-one mapping between the forcing and the response. This is not the case for fluids because fluids couple to rotation, so you have Coriolis effects. And add to that, fluids couple to the surface, and if there's boundary conditions on the surface, which is the case imposed by the terminator blocks motion into the night side, then this allows for scattering a single gravitational mode into a family of modes, and you have a multimodal response on the surface. So you go from one mode to a spectrum of modes that manifest as families of lava waves migrating and moving around on the surface, on the dayside surface of the planet. So we're going to see how do these lava waves manifest on the surface in the following plots. So what I'm plotting here is the surface of a planet, taking the fiducial case of 55 Cancri as a case study, and I'm plotting a heat map of the surface, just the temperature. This is the color bar, allowing for both stellar irradiation and tidal heating, so the generation of these tidal waves. And I'm going to allow the planet to orbit around its star for a few orbital periods, and then we're going to change the eccentricity of the planet because that basically controls the strength of tidal forcing. So for very low eccentricity, we see what we expect from stellar irradiation. A hot spot anchored to the substellar point, and then you freeze out as you go to the terminator. This is basically just the daytime. And that's because tidal heating is very insignificant in this case for this low eccentricity. Now, and if we capture all that into the surface equilibrium temperature, we just have a fraction of a degree variation. In red, you have only that driven by insolation, and we add the effect of lava tides with yellow, and so there's not much difference between the two curves. Now, add the effect of, increase the eccentricity a little bit, just to 1%. We're not talking about a crazy amount of eccentricity. And then you start seeing the effect of lava tides. So you have lava waves migrating eastward and westward on the surface, and they decouple basically the hotspot from the substellar point. And that's just for a 1% eccentricity. Now, and then you start seeing a distortion in the evolution of the surface temperature. This is for 10 orbital periods. Now add the eccentricity a little bit more, just for a few percent, and then things go crazy. Now you have families of lava waves on the surface, which are interfering with each other. Sometimes they constructively interfere, so you generate thermal pulses. Sometimes they destructively interfere, so you go back to the thermal state driven by insolation. And then you lose, more importantly, you lose so the hotspot is just wandering around eastward and westward, mostly eastward because of how tides behave. And you basically lose the periodicity of the signal. So this is the thermal state dominated by these lava tides. The temperature is erratic, it's bursty, you have these thermal pulses, and more importantly, it's aperiodic because of this interference pattern, which generates in frequency analysis a beating pattern between the waves. And so if we capture these thermal states stroboscopically, just like we do in eclipse variations, this is the range of a variation of the longitude of the hotspot boxed in these boxes, and the temperature, surface temperature, as a function of eccentricity. So you can naturally and easily get tens of degrees variation in the hotspot, longitude of the hotspot, and variation in the temperature as you see different eclipses at different orbital periods. So I don't think I have time to go. How much time do I still have? 2 more. Okay, so I do have time, unfortunately.
Okay, so that's just to say that we also took into account this fluid deposition of energy on the surface into the interior and how does that shape the interior. And so just imagine having at first just an insulation-driven magma pond. So that's the skin-deep magma pond that we can imagine driven by insulation. And then we allow for these lava waves to move into this very thin layer, and they slosh around and deposit energy in the process. And they deposit energy mainly at the bottom of this ocean. And so they start depositing energy and melting more and more of the mantle until they reach a level where you balance that by convective cooling. So you reach a very thick magma ocean instead of a skin-deep magma pond. And that's only by taking the effect of this fluid lava tidal heating. And for super Earths, what you end up with is a very thick magma ocean, thousands of kilometers deep, on top of a mushy layer, on top of a solid viscoelastic mantle above the core. But for Earth-like planets, you'd be able to melt the whole mantle as long as you can maintain tidal force. So that's a way of digging deeper and deeper magma oceans just by taking into account this effect of fluid tidal heating. So I hope I've convinced you that taking into account this effect is very significant for our observables, and I'm going to leave you with my takeaways, and happy to take any questions. Thank you.
Brilliant. Thank you. Very interesting talk, and for sticking to time. Gosh, there's a lot of questions. I think you were first there.
Hi, this is Kaustubh Hakim from Lebanon, Brussels. Brilliant talk. It was very convincing. I actually have a question one step further connecting to the previous talk. So you consider tidally synchronous situation, right? But if you have a 3-2-2 resonance, how would it affect? Does it complicate the situation?
Yeah, you have more variability with 3-2 resonance because you have stronger tides.
Okay.
So these are eccentricity tides, which are weaker than what we call asynchronous tides.
So potentially you can match the temperature.
Oh, very easily.
GCRM show.
With asynchronous rotation, very easily you would do that, yes.
Fantastic.
Okay, one more question, and then lots on Discord. At the front here. Sorry.
Hi, Laura Kreidberg, MPIA. Great stuff. I am wondering if you could comment on the results of the previous talk from Jayshul showing those very large wigglies in the light curves, the thermal emission coming from 55 Cancri E. As an observer, I would guess that those are instrument systematics, but have you looked at whether the timescale and the amplitude of those are consistent with your predictions?
Yeah, the time scale certainly, so I try to be very careful in the paper not to say this is 55 Cancri today, although we took that as a fiducial case. But certainly the time scale match because tides are on orbital periods. That's the characteristic time scale of tides. And you can even get suborbital periods because these waves have shorter periods. The problem is we need to maintain a source of tidal forcing for 55 Cancri, which in the absence of asynchronous rotation and eccentricity would shut off the tides. Now 55 Cancri has outer planets that can maintain eccentricity, but they're not in the place where we would like them to be. Yeah. So I wouldn't say something specific about 55 Cancri yet.
Fair enough.
For the question.
Okay, maybe time for one very quick question while we just wait for Tim to come back. Is there one there? Right. Okay. It's just there. Okay, release.
Okay, I can hear you. Yeah. The initial condition. Yeah, so we do not determine. Yeah, so the results we obtain are irrelevant of that because looking back at these thermal balance equations, you can start at, so this is a orbital period versus the adiabatic profile of the interior. And so if you start anywhere, it's just, you're either gonna cool until you reach an equilibrium or you're gonna heat until you reach an equilibrium. So it doesn't matter, you just will eventually get into a stable equilibrium. So it doesn't really matter what initial condition you're on.
Okay, brilliant. Well, let's thank all the speakers from this session.
Thank you.
1 minute, 1 second.
All right, so this is the first advertisement for this dinner. The first thing is, if you don't know if you registered for dinner, you can check at the registration desk. There's the registration list, and you see if you registered for dinner. So please go check that out. So the dinner tonight will be at the NOC, which is at the top of the forum, Groningen, which is this building here. And so essentially, it's pretty simple. Go into that thing and use essentially the staircases and go all the way up. It's actually quite some journey, so I encourage you to really enjoy it. So if you were in the middle of the city, in the center of the city, at the Grote Markt, which is here essentially, this is how it would look like to you if you were on foot, pedestrian, you know, and then you would go there. Then the entrance to this thing is on the right side, like here, and then you enter this thing, and then you just use all those escalators essentially. Just go all the way to the top, and then you reach the NOC. This is the address, and we'll start at. Please be there sometime between 7 to 7:20, 7:30 or something like this. So we have an apéro in the beginning, and then food starts at 7:30. So this is this. Thank you so much. And now what we will do, just before lunch now, we will do the conference photo. And for that, please orderly try to get up and try to get out of this right-hand side here. And then we will do the conference photo on the stairs to the right and on the first and second level. And so there will be LOC members standing there. And then we will take this photo. We all look very happy. And then we will all have lunch, okay? Thank you so much to the speakers and to the chair of the session.
For a secondary atmosphere. Here's a figure from Hu et al.'s 2024 Nature paper. They reported emission spectrum from obtained by NIRCam and MIR observations. On the right panel, the observations, the points of these error bars are observations, and the color lines are their retrieval model result in different compositional scenarios. And the panel B shows the posterior distribution of their retrieval model. Here they show the free parameter, surface pressure, and log CO2 volume mixing ratio. And their results suggest the atmosphere is secondary and probably rich in carbon monoxide or carbon dioxide. And more recently, a more comprehensive 1D forward model was implemented by Zelinskas et al. And their model have incorporated with equilibrium chemistry. And their model suggests the atmosphere might be rich in phosphorus monoxide or carbon dioxide. And you might ask, the previous model have very well interpreted the data. Why I'm here to reanalyze it. The key movement is the heat redistribution efficiency. Oh, thank you. Oh, sorry. The heat redistribution efficiency is a concept to describe how efficient the atmosphere transport heat from day side to night side. Here we use the definition of the day side brightness temperature. previous analysis have already suggested that the Meteorite data is highly consistent with high efficient distribution efficiency scenarios. But the previous 1D model cannot resolve it. And they set the heat redistribution efficiency to a free parameter in their retrieval model or just fixed when they analyze it. So this is where the 3D general circulation model comes in. 3D general circulation model GCMs can simulate self-consistent heat redistribution because they can simulate the atmospheric dynamics in a 3D global grid. However, so far, no GCM with realistic radiative transfer has been employed for feedback Cancri. This is because standard GCM radiative transfer cannot simply apply to high temperature atmospheres. This is because the lack of absorption lines and the line profile changes a lot with temperature. So therefore, we want to tackle this problem by compute custom correlated K coefficients for high temperature atmosphere and run a GCM with a long-range radiative transfer. What we do first is we compute, we compute absorption cross-sections from absorption line profiles. We use the line profiles from ExoMol database and use a program ExoCross. Here shows the CO2 absorption cross-section at 300 Kelvin, Earth temperature, and lava planet 2,500 Kelvin. And the x-axis is the wave number in centimeter inverse. The y-axis is the cross-section. And you can see the difference between Earth temperature and high temperature is very large. And then with the absorption cross-section, we also include the UV absorption cross-section from ExoMol and a collision-induced absorption cross-section from Hydron. And we compute the correlated K from the cross-sections and run a GCM ISCA coupled with Socrates. And by the way, if you want to know how correlated K method works, you can come to me during the break. I can explain to you. Okay. And here's our result. There's a video shows how the temperature and horizontal wind changes with half surface temperature changes with time. When we find the simulation suggests the atmospheric dynamics is dominated by the effect of a stationary Rossby wave in the mid-latitude and the Kelvin wave on the equator. And then we've used the GCM output to compute the emission spectrum. We derive it via the observer projected flux integrated from the whole dayside atmosphere. And here's the emission spectrum we derived, and the color lines shows the best fit case in each compositional scenario. We tested pure CO2, pure H2O, pure CO, and CO2-CO mix and CO2 nitrogen mix scenarios. And here I want to emphasize that the near-cam offset is a free parameter because the observations find strong correlation noise. And we analyze the goodness of the fit via the chi-square. Via the chi-square, and here I show the chi-square of all my simulations. And the x-axis is the surface pressure. We do simulations from 0.01 bar surface pressure to 100 bar. And we vary the CO2 volume mixing ratio for the nitrogen and CO background atmosphere. And the chi-square value highlighted in red means they have a significance, p-value larger than 0.05. And the gray crosses suggest the atmosphere is so cold and it might collapse. And we further separate the chi-square to different bands. And we further explain the myriad observations with heat redistribution efficiency. And we find the myriad has a strong constraint on the heat redistribution efficiency, and only 100 bar atmosphere can fit the observation well. And we further propose that previous 1D model have overestimated the heat redistribution efficiency
In Huatov's paper, they propose the 10-bar atmosphere is full heat redistribution. But in our simulations, with self-consistent calculation, we find the heat redistribution is parameter is 0.5. And here I want to talk a little bit about the variability. As Jishel talked this morning, and the planet eclipse that shows strong time variability. And we further wonder if the atmospheric dynamics can produce the time variability, but unfortunately not. Here shows the brightness temperature changes with time. Because our simulation is a clear sky, so this is only due to the large-scale atmospheric dynamics, and the brightness temperature time series is very flat and much weaker than the observation from 800 to 2000 Kelvin. And here's the take-home message. I'm happy to take questions.
Amazing. Thank you so much. Any question for Ray? Yeah, we got one here in the front.
Hi, this is really nice. Ted Kamasik, Oxford. Yeah, really impressive undertaking doing a hot rocky planet GCM with non-gray rate of transfer. My question is, you have a nice fit to the JWST data, but there's also a Spitzer phase curve that's been compared to GCMs. Have you compared to the Spitzer phase curve, and does your best fit models also match the Spitzer phase curve?
I haven't fit the phase curve because previous studies find the interpretation of the offset phase curve is challenged. I remember there was a paper in 2022. So I think the observation is not that confident. So I didn't.
That makes sense.
Thank you for your question.
Okay, any other questions? Questions from online, maybe? No questions? We have one question here.
Hello, Tina Neumann from GFZ Potsdam. Just a simple question about your model. What are your boundary conditions? Because I didn't see periodic or...
Thank you for your question. Our model has a surface, and we have surface roughness, so it will dampen the surface, and we also have a TOA sponge layer. And yes, left and right. It is a global, global climate.
Okay, any other question?
Hey, Chris Worth from University of Chicago. This is super cool. You said that the surface, it just has roughness. How would you don't do any sort of like lava ocean resolution, or would you, like, what would you say would be the effects of including like the magma ocean on the dynamics?
Oh, very, very interesting question. Yes. No, the surface actually, I set it to a slab ocean and set some roughness similar to a rock like Mars. And yes, but I think in the future we should include some interactions in the surface between surface and atmosphere.
All right. No more questions. Okay, then let's thank Reju one more time. Okay, and our next speaker is Carlos Engin from the Freie Universität in Berlin. It's getting packed.
Okay. Hi, folks. How are you doing? Woo! I'm Engin Carlos. I'm a postdoc from the Freie University Berlin. And my big aim now is to convince you folks that also ground-based high spectral resolution observations can characterize hot, rocky exoplanets. Yeah. Before starting, I would like to acknowledge all the collaborators from this project, and especially also the INAF and LBTB tags from the AIP, which made these observations possible. Yeah, let's start. So lava vault planets, as we heard from several talks, have molten surfaces, and we always ask ourselves, what kind of atmospheres can these molten surfaces, lavas, produce? And during the transit of a planet, you can see these thin atmospheres, and we, of course, try to probe them. The first question is, what kind of atmospheres can they produce? I'm going to because you have always this echo from this position. Did you get it? Okay. The initial lava pool can consist of different types of rock compositions, like big bulk silicate earth or oceanic or mercury. And the initial composition, of course, determines the atmospheric composition in the end. However, the initial composition depends also on the interior, as we also learned from Charles-Edouard Bouqueret. And the efficiency of replenishment of species to the lava pool will determine, of course, the atmospheric composition. So how does the initial lava pool composition change over time? So here's shown a figure from Kite et al. You have a mole fraction of different species over the, let's say, melt pool evolution. So what you do in the beginning of evolution of a magma pool, imagine you don't have replenishment from the interior, very inefficient replenishment. You release sodium and potassium, and thereafter magnesium and iron stuff. But for a long period, you get still a lot of magnesium oxide and silicon dioxide in the atmosphere. So assume now an initial composition on such a lava planet with also some recycling going on. You would have, if you have also volatiles, maybe a lava pool like this. However, in any case, you get a lot of magnesium oxide in the atmosphere of such lava vault planets. So one good thing of magnesium oxide is it has a lot of absorption bands in the optical wavelength range. Now let's go to the extreme. Let's think about what happens if this soup cooks all the time and don't get some refilled with elements from the interior or from the underlying melt. So when we end up in this position here, where you have a lot of aluminum 203 and calcium oxide. In that case, if you don't have replenishment from the interior, what you get out is maybe a slow cooking lava pool with some thin atmospheres, but you still get a lot of aluminum oxide in the atmosphere. And also here, the benefit is aluminum oxide has significant number of absorption lines in the optical wavelength range. So why I'm speaking about this? If you speak about ground-based observations, you use usually the cross-correlation method to deduce absorption fingerprints of elements. So what happens is here is shown the transmission spectrum and an imprinted absorption spectrum here. And when you move with your template, and if you match the planetary absorption imprinted in the transmission spectrum, you get a peak. And if you don't have something, you get noise. In this case, with the amount of absorption lines, your species you investigate have, or emission lines. If you do eclipse observations, you use emission. If you have absorption, transit observations, you use absorption template spectrum. Okay, so now, long story short, what we did, within the hardest project, we observed 15 transit observations of 55 Cancri at the LBT, the Large Binocular Telescope. The Large Binocular Telescope is one of the largest facilities on Earth. It has 2 × 8.4 meter mirrors, so 4 or 5 of us can lie down and would match the diameter of one of these mirrors. So I'm showing now some results, which I denote as preliminary because we are going to submit the paper within 2 weeks. And yeah, now let's see if we see some aluminum oxide and magnesium oxide in the atmosphere of this planet. First of all, this is the transmission spectrum. So this is the fingerprint of the planet from the 15 combined LBT observations with some telluric regions masked out. And the observations have been taken in the course of 4 years, but most of them are taken in the last 2 years. So let's see. This in the lower part, I am showing the magnesium oxide template, and in the upper part, I am showing the signal to noise of the detection or non-detection. And what you want to see is a peak around the zero RV position. Boring. Huh? Okay. So there is no evidence of magnesium oxide. But what do we expect for a planet like 55 Cancri E? Let's have a look to the aluminum oxide. Ooh. Can you do it again? So there is an interesting signal arising very close to the planetary radial velocity position. So of course, the first thing you ask yourself, features like this can come and go, you know, in cross-correlation analysis. You have to be very careful. Is this a trustworthy signal or not? Then what you do usually in the high-resolution community, you check if the signal vanishes out if you change the planetary parameters. So you expect the signal, of course, only arising at the correct orbital velocity of a planet. So you do several cross-correlations. So the planetary velocity is around 230 kilometers per second. And this is like showing what would happen if we change the velocity to plus minus 100 kilometers per second to produce this combined transmission spectrum. So you see in a feature or arising only at the planetary radial velocity position and planetary orbital velocity, with a Gaussian distribution of the signals here being very smooth. So, but of course, still we think about more sanity checks, yes? What happens if you combine nights? So we saw in the eclipse spectra, and also as Jaishal Patel showed us, there are some variations in the eclipse data which you don't usually see in the transit observations, but we should check if we see this signal increasing, combining more and more nights. So this shows for 4 nights, you don't see a very significant peak. Now have a look to 8 nights, 12 nights, and combining all observations. So there is a real strong increase of a detection peak at the expected place of the planetary rest frame. Okay, we did several other sanity checks. If you are interested in all of them, how it changed with wavelength dependence, how it changed with different methodologies and so on, feel free to speak me. But how do these observations now compare to the LBT results? So we saw this plot, I guess, today 3 times or 4, and also the whole week. But let's maybe compare first to the NIRCam observations, which propose a volatile dominated atmosphere. Of course, an evolved magma pool and volatile atmosphere from the same magma pool originating is a bit difficult to explain, I guess. But what could, of course, always be the case is that you have like volcanic eruptions going on, and then you see some heavy volcanic eruption filling the atmosphere with volatiles. I think some modelers would need to model this to show if this is like possible. But we also have, as shown in two talks before, that we see a lot of variability going on in the atmosphere. Okay, besides the NIRCam observations, we have VMIRI observations, yes? The VMIRI data show a colder day side. How does the LBT observations match with this outcome? So what you could have is, of course, a proposed feedback by Loftus et al. Recently, changing cloud coverage on the day side. So you build clouds, you cool the surface, the clouds get distracted, you heat the surface, you build clouds, and so on. So this could, of course, explain the MIRI data and would be also consistent with the aluminium-203 melt pool, which could release this species and build or be likely part of the cloud layer. Okay, and more things to matching the aluminium oxide into the big picture is the low density of 55 Cancri E could be explained by a coreless planet enriched in aluminium and calcium if a planet is formed very close to its host star. In that case, it would be enriched in aluminium also explaining the large aluminium-203 content of the melt. Next to this, aluminium-203, as mentioned, could be the likely source of the cloud coverage proposed from the magma temperature cloud feedback. And lastly, some of the investigations assuming lava vault planets with inefficient heat distribution, if we now go from the efficient one to the inefficient one, propose high wind velocities and also like decreasing terminator temperature at the from the substellar point to the terminator, as you see here. And our best match templates, so we tried out different templates correlated with the data, hint on a colder terminator temperature as proposed here. And we also see some strong wind velocities, which also agree within 2 sigma with these velocities proposed here. Stop. And I am done. This was the initial question. What about the melt pool evolution? And we have a strong hint on inefficient replenishment if there is no other scenario which can explain this. And I leave you with the conclusion that's saying that hot rocky planet atmospheres can be detected with ground-based facilities, also verifying for the first time the existence of a lava vault planet with the detection of atmosphere. And probably 55 Cancri has an evolved magma pool made of rubies and sapphires. Okay, thank you very much.
Amazing. Thank you for the great talk. Okay, I see many questions. Let's take those three here. Please be brief with your questions and answers. Thank you.
Hi, thanks very much. Xander Byrne, University of Cambridge. We've seen that from some of the previous talks that the situation on this planet in general is quite variable with time. So I was wondering whether you tried where you were stacking the observations from different nights and seeing that over 12, if you do 12 observations, then it looks better than if you do 8 observations. I wonder whether it depends on which 12 observations you choose, and whether if you choose different kind of subsets of your observations, the cross correlation gives a different significance.
Good question. In that case, we stuck them together in the order of the observation. So it was not like choosing the ones which match better the data. So it was like the first 3 observed data sets stayed together, the after was the first. The thing of Pepsi is you don't have a coverage of whole wavelength range in one. So you have different resolution modes. We have always different wavelength ranges. Yes. But I did the analysis once to iterate all the 3,000 different iteration possibilities for 15 observations, because we have also different cross dispersers. So we always observed at different wavelength ranges. And the tendency of increasing was always there. Yeah.
Thank you.
We are not going to be able to take another question. So if you have more 55 Cancri questions, I suggest you gather at the break outside and have a 55 Cancri group chat. Thank you. Okay, and our next speaker is Anna Bongad. I hope I pronounced this correctly. Is from the University of Birmingham.
Hello, everyone. My name is Anand. I'm a second-year PhD student at the University of Birmingham. And today I'm going to talk about could we distinguish between endogenously produced versus accreted volatiles in sub-Neptune atmospheres. So we all know that super-Earths and sub-Neptunes are the most common type of exoplanets detected so far. And yet no analogs exist in our solar system, making them interesting targets to study planetary formation and atmospheres. So the mass radius relation for these planets show that these planets with similar masses can have different sizes, implying that these planets could have wide range of bulk composition ranging from rocky interiors to water-rich planets, implying that it is difficult to infer interiors just on the basis of planetary mass and radius. So atmospheric spectroscopy reveals chemical fingerprints and such as volatile abundances and outgassing products, which is linked with the planetary interior. So the atmosphere can act as a window to probe planetary interiors and help to place a constraint on its structure and composition. So JWST has provided with high quality transmission spectra for several sub-Neptunes. JWST's high sensitivity and broad wavelength coverage enables it to detect multiple features of some molecules, hence confirming their presence. And these data have started to place an initial constraint on internal structure and atmospheric properties of sub-Neptunes. So water, carbon dioxide, and methane are some of the major volatiles that has been detected in sub-Neptune atmospheres. But the key question remains, where do these volatiles originate? So volatiles can either be produced endogenously by atmosphere-magma ocean interactions, or it could be accreted as ices beyond the snow line during formation. In addition to these processes, it could also be, mass loss mechanisms could also enhance heavier volatiles in the atmosphere. So the main focus of our work is, could we distinguish between endogenous versus accreted volatiles in sub-Neptune atmospheres? So to do this, we use a global chemical equilibrium model, which was explained by Ariel in his talk yesterday. And we use the same model, and quickly going over through it. So it is based on Schlichting and Young model, in addition with a reaction which captures the carbon partitioning in metal phase. So it is basically a zero-dimensional model, which enforces chemical equilibrium and elemental conservation across atmosphere, mantle, and core. to calculate equilibrated abundances. It takes in species, the mole fraction of different species, the number of moles in different phases, the temperatures at atmosphere magma ocean interface and silicate metal equilibrium boundary, and mass of the planet. So in future, we are going to use the atmospheric abundances from this model as inputs to 1D atmosphere model to see how it translates into chemical abundances in observable atmosphere. So these models have been previously used to study volatile production by atmosphere interior interactions. For example, Nixon and others and Benek and others have used these models to explain the JWST observations of TI 270D. And according to their results, the atmosphere magma ocean interactions could reproduce the observed metal-rich and carbon-oxygen-bearing atmosphere. So moving on to what we did. So in addition to endogenous scenario, we also explored accreted scenario. So for accreted scenario, we varied the amount of accreted volatile from 2 to 10% by mass. We explored two cases, one where we only accreted water. Second case where we accreted a mixture of water and CO2 in 3:1 ratio by mass. We used TOI 270D as a test case. Our initial assumption for the planet was 2% atmosphere by mass with 1 time solar metallicity and an Earth-like mantle to core ratio with magnesium silicate-rich mantle and iron-rich core. In addition to that, we also explored reactive core scenario where all the three phases, that is atmosphere, mantle, and core, interact with each other, and an unreactive core scenario where only the atmosphere and mantle interact and the core doesn't participate in any interactions. So moving on to the preliminary results. So first we explored how the volatiles partition as a function of interior temperatures. So these plots are for 10% accreted water plus carbon dioxide scenario. On the bottom x-axis, we have temperatures at silicate metal equilibrium boundary, which is 500 Kelvin hotter than the atmosphere magma ocean interface temperatures. As we move to the right, these temperatures increases in the steps of 500 Kelvin. So on the left for the oxygen, we can see that as we increase the internal temperatures, the oxygen in the atmosphere and mantle decreases because it is getting sequestered in the core. Whereas for the carbon, no matter the internal temperatures, the carbon gets sequestered in the core with higher mass fraction of carbon going in core at lower temperatures as compared to the higher temperatures. So from this plot, we can see that how both these species behaves differently with the increasing internal temperatures. So next we explored how the volatiles partition as we increase the amount of accreted volatiles, and we fixed our AMOI temperature at 4000 Kelvin and SME temperature at 4500 Kelvin. And first we explored accreted water only scenario to check if the atmosphere is sensitive to accreted oxygen. On these plots, on the x-axis, we have amount of water accreted. On the y-axis, we have fraction of oxygen in each phase related to total moles in planet. So on the left for the unreactive core, as we increase the amount of accreted water, the oxygen in the atmosphere increases and it decreases in the mantle. In this scenario, as core doesn't interact at all, the carbon, which is present in trace amounts initially, remains unchanged, and it is not shown here. On the right for the reactive core scenario, as we increase the amount of accreted water, the atmospheric oxygen stays nearly constant. This is because a high amount of oxygen is getting sequestered in the core. And from these plots, we can see that how atmospheric oxygen behaves differently depending upon the different core reactivity. And from this plot, we also find that, that the atmosphere is sensitive to accreted oxygen, but only for the unreactive core scenario. So next we move on to accreted water plus CO2 scenario to check if the atmosphere is sensitive to accreted oxygen plus carbon. And these plots are basically similar to the ones which I showed you for accreted water only scenario, with the only change in the x-axis, which now has accreted water plus carbon dioxide. And again, the oxygen, the atmospheric oxygen shows the same trends as we saw in for accreted water only scenario, where the atmospheric oxygen is increasing with increasing amount of accreted volatiles in unreactive core scenario. And the atmospheric oxygen stays constant for increasing amount of accreted volatiles for reactive core scenario. Next, we move on to carbon. So for carbon, as we increase the amount of accreted volatiles, the carbon in the atmosphere increases initially and then it plateaus, but it stays dominant in the atmosphere. whereas on the right, for reactive core scenario, as we increase the amount of accreted volatiles, the atmospheric carbon again initially increases and then it plateaus, but it is dominant in the core. So depending upon the core reactivity, though the atmospheric carbon behaves similarly, but their abundances are different depending upon the core reactivity. Also from this plot, we see that the atmosphere is sensitive to accreted oxygen plus carbon. So atmospheric C2 ratio is something that could be measured from observations, and it could potentially be used to distinguish between endogenously produced versus accreted volatiles. So on this plot, on the x-axis, we have amount of accreted water plus CO2. On the y-axis, we have atmospheric C2 ratio. And we can see that the atmospheric C2 ratio increases for both the reactive core and unreactive core scenario. There is a difference between the values between these two scenarios. This is because though carbon increases in both the reactive and unreactive core scenario, but the oxygen, which nearly stays constant in reactive core, and in unreactive core, it increases, which is why it causes this difference in the atmospheric C2 ratio. So our main question was, could we distinguish between endogenously produced versus accreted volatiles in sub-Neptune atmospheres? And we find that volatiles accreted during formation don't necessarily show up in the atmosphere because it gets easily sequestered in the interiors. But it could potentially be distinguished if the core is unreactive and or if carbon is also accreted. So our next steps is to model JWST observability using 1D atmosphere model. Thank you for listening, and I'm happy to take questions.
Thank you. Any questions? I've got one here.
Hi there, thanks for the talk. Rob Calder, University of Cambridge. So you've talked about the differences in the atmospheric content based on the reactive and unreactive core. What determines whether the core is reactive or unreactive?
So we can't figure, we don't know whether the core is reactive or unreactive. We just use an extreme scenarios where it is either unreactive or reactive. And then we explore in future, how changing the percentage of reactivity, how it would affect the atmospheric abundances.
Okay, thank you.
Thank you. Other questions? Is there any questions online? No? Yes, there's one more here.
Madeline Broom, UC Santa Cruz. Is this specific to CNO chemistry, or could we be using other tracers for this reactive and unreactive core scenario?
So what other species?
Other species.
I mean, because the model only has simpler, so it has very few elements to work with. So that's why as a start, we are using carbon and oxygen. But if we could add more and more reactions, volatile, which produce volatiles, then I guess we could be able to include that and see how it behaves.
Okay, let's thank Anand one more time. Okay, and our next speaker is Takanori Kodama-san from LC Science Tokyo.
Can you hear me? Good, okay. So hello everyone, I'm Takanori Kodama from LC Science Tokyo. Today, I'd like to show and also share our preliminary result about the cloud distribution using GCRM. GCRM is kind of new generation GCM. It takes account cloud microphysics with super high resolution simulation. First of all, as you know, when we discuss the habitability on the exoplanet, we can use the concept of habitable zone, right? This concept of habitable zone calculate estimate by the 1D simulation. But recently, the terrestrial planet around the Roma stars gradually became prime target. And also, thanks to the their clouds in orbit. These planets expect to be a tidal rock state. The characteristic of this planet has permanent day side and night side. So it makes a strong day-night temperature constant. Yeah. So such kind of the strong day and night temperature constant makes very different the atmospheric circulation called day-night circulation, and also typical cloud structure on the day side. Thanks to the previous studies, they pointed out the importance of cloud feedbacks. So on the previous studies, the cloud makes planetary albedo higher to protect surface environment. On the other hand, with the rapid increase of our computer resources, we can easily access supercomputer and we can carry out a little bit heavy simulation on supercomputers. So this is an example of the climate of the Earth with 3D global cloud resolution model with 3.5 kilometer mesh resolution, which take account the cloud microphysics. We cannot distinguish between the simulated data and the real data, right? First of all, I have to explain the reason why do we need GCRM in exoplanet climate. The traditional GCM will treat cloud formation by divide into two. One is the large scale condensation, the other is the cumulus convection parameterization, depending on the scale of the GCM grid. So that kind of GCM tells us the information about cloud fraction and cloud coverage with a GCM grid cell. On the other hand, GCRM can directly simulate cumulus convection and tabular scale motions. And also, we can launch a GCRM simulation with cloud microphysics with 6 types of cloud. So it can resolve the convection and cloud. In the other words, it can estimate and investigate the interaction between cloud and dynamics, and also the interaction between the cloud and radiation. So we try to apply this kind of GCRM to exoplanet tidal rock planets. I mean, to comparison, here is the, let's say, setting from the previous studies with low resolution and cloud parameterization. Here is our setting. We set some planetary parameter to be a TRAPPIST-1e case, and also we use GCRM named NICAM. Here is our integrated period, around 3 years to get the equilibrium state. Here is a resolution of horizontal scale around 10 kilometer mesh in global scale. And this is a number of vertical layers. We assume 78 layers in the vertical. So total grid points around 200 million in total. So we just one simulation, we need a millions of nodes overall, right? And also we take account cloud microphysics at the same time. So in this case, we use a single moment scheme with 6 types of cloud, which include real water vapor, cloud, ice, and also snow and globules, something like that. So these panels come from the previous studies with a low resolution and also cloud parameterization. These results, we already know, thank you very much. And if we launch a simulation, GCM simulation is super parameterization, we can see more 3D cloud structures. This is a super parameterization method. Super parameterization, we launch simulation with low resolution first, then we can launch a cloud resolution model inside, within the GCM grid cell. Then to the cloud resolution model, bring the external first term to the climate side. It means that climate model does not directly link to the cloud microphysics. So it's time to run simulation with GCRM. This is our first result about the cloud distribution for the assuming TRAPPIST-1E case. You can see very beautiful cloud distribution, right? And here is the day side, and here is the night side. As you can see, we confirm the very thick cloud around substellar point, like the previous studies. But we can see very, very fine structure of cloud of cloud and distribution of cloud. Then also we can see, our simulation pointed out the presence of cloud on even the night side. This is kind of comparison with different orbital period. This result is the same as the previous slide, assuming TRAPPIST-1E case. Then we run the same simulation with different orbital period. We can see completely different cloud distribution details. And if we run the simulation with a longer orbital period, we cannot see any cloud on the night side. So our simulation suggests that the habitability, of course, it strongly depends on the stellar flux from the central star, but super important to discuss the rotation rate, let's say, dynamics of the planet. And also, you can see here is a terminator region. Depending on the orbital period, we cannot see the cloud of the terminator. So our simulation suggests that we have to see any water vapor around the terminator region from the GCRM. Here is a summary slide. Of course, already you know, tidally block planet, terrestrial planet around Roman star is a prime target for the habitability of planet and also the future observation mission. So it's time to introduce a new generation GCM called GCRM to take account the cloud microphysics at the same time to investigate interaction of cloud dynamics and the cloud, radiation and the cloud. As a result, we can see more detailed cloud structure and cloud distribution. So we can treat the feedbacks between the cloud, water vapor, and the dynamics. That's all for me. Thank you very much for the presentation.
Thank you. Okay, any questions for Kodama-san?
Hi, Mara at the Captain Institute, Groningen. Thanks for the very nice talk. Very quick question. So what about like computation time of GCRMs versus classical GCMs? And do you absolutely need then to be on a supercluster? And what do you do if you don't have access to those?
Okay, this time we use the Fugaku supercomputer. It's the fastest computer in Japan. And it takes, for example, it's so independent schedule of Fugaku that it takes 3 months. And just one shot. Do you understand, right? So yeah. And also it needs a million node hours, let's say, just one shot. Yeah.
Excellent. Other questions? I think Ted has one question.
By the way, this is the first, that's how to say, the highest resolution in the 6 prime size. Yeah.
Hi, Takamasik, Oxford. This is outstanding. My question is about the surface boundary condition.
Okay.
You have an aquaplanet surface that's supplying the water that then makes these clouds. My question is, how do you treat that ocean?
First, the setting is aquaplanet formation. So a planet is covered with the ocean. And we set the one meter depth of mixing layer, like about, sorry, buckets model.
Follow up, do you allow for sea ice formation?
I did. So we can see the distribution of sea ice as well.
Okay, we had one question here.
Hey, really cool talk. Hannah Birkbeck from University of London. Have you compared these results with like core scale GCMs, like let's say looking at TIE and things?
Now calculation is started to compare with the TIE project or some previous GCM studies.
And then also like looking at some of Denis Sergeyev's work as well, when he's also looking at explicitly representing clouds and things as well. Have you also compared with that?
Not yet.
Okay.
Yeah, thank you very much.
Okay, any other questions online? Then let's thank Kodama-san one more time.
Thank you very much for the attention.
Okay, and our next speaker is Bennett Skinner from McMaster University.
Hello, can everyone hear me? All right, today I will be talking about a solar system validated rocky world interior structure model and new mass radius relations. Here are the new mass radius relations. If we look at these new mass radius relations, we can see that along this green curve, where for each of these different curves, the different colors tell us different compositions, and as we go left to right, we're just changing the mass, giving us different radii and thus different densities. So we can see that along this green line, we have Earth, we have Venus, we have several other solar system objects, and we have a bunch of super-Earths. So super-Earths look, at least broadly, Earth-like. We see Mercury is clearly denser than that line. That tells us that it's iron-enhanced. And we see even that the water-rich moons of Callisto, Titan, and Ganymede are compatible with being about half water by mass. If we zoom in a little bit on the Radius Valley region, and we look at sub-Neptunes, we can see that this is the region where our water-enhanced and hydrogen-helium-enhanced lines overlap, telling us that the sub-Neptunes could have a significant amount of water, or they could have a significant amount of hydrogen-helium. But I'm not telling you anything new, so who cares? Well, over time, the observational restraint that we've had on the radii of small planets has slowly become more and more accurate. And we're kind of plateauing, although some of the best observations are able to get better than this, at an error of about 2% at 1 sigma, where we're ultimately being constrained by our uncertainty in the radii of the stars. So any model that we have for the radius of a planet should have an inaccuracy due to any assumptions we made in the construction of that model that is less than 2%. That way, observational inaccuracies are much larger than our theoretical inaccuracies, and it's comparatively much, much easier to tell us what an observational uncertainty is than a theoretical uncertainty. So, is that true? Here you can see in 3 different cases, a solid line is the mass radius curve generated by our model, and the dashed line is the one from Zhang et al. 2019, which is the most common curves used in the literature, but don't think that this only applies to one paper. I'm just using it because it's the most common. I have for 3 example planets shown one that matches exactly our forward model with realistic uncertainties on their masses and radii. And you can see that at least the 1 sigma level, these 2 curves are different for all of them. And this difference can actually lead us to have incorrect interpretations about what the nature of these objects are. So for example, this one up here, if we're comparing it to the dashed line, it clearly looks like it's above this half water mass line, which makes us think that there has to be some amount of hydrogen-helium present. But if you're looking at our curves, you actually see that it's completely compatible with just having half water by mass. If you look at this curve right here, it looks like it's clearly above the Earth line, so you might think that there's some volatiles there, but actually that change in density can just be explained by the mantle being in a molten state instead of a solid state. And finally, for this planet at the bottom, it looks impossible using the old mass radius curve in the literature, but using our new models, you can see that it's just a pure iron core. These are, of course, kind of 3 extreme cases, but this is to illustrate how important it is to actually use the most up-to-date mass radius relations. So, simplifications in literature interior structure models lead to incorrect inferences about the nature of planets. What have we actually changed in our model? There are a lot of things, but I'm going to focus on 3 key things for time here. We have more complete chemical inventories. We have more phases of all the materials within our interior structure. And we have new equations of state that are coming from many advances and experiments and simulations that allow us to probe higher pressure regimes than were previously possible. There's also other things that I don't have time to talk about, but you can ask questions if you care. I'm now going to proceed from the outermost part of the planet to the innermost part of the planet and give a brief description of the things that we've updated. So for the envelope, it's not just a hydrogen envelope. We also have helium, and we have non-ideal mixing between the two. The net effect of this is a systematic reduction in density, at least for the low planet masses that we care about at rocky worlds. For water, we use the aqua model, which the most important effect that it has is it lets us have a steam atmosphere, but I won't dwell on it too much because the aqua model has already been talked about quite a bit. The mantle is where things get messy. So here's the phase diagram for the mantle. This is for everything, and then on the right, we have multiple zoom-ins to different parts of parameter space. I'm just going to talk about some key points, but as you can see, there's a lot of complexity that I'm smoothing over here. The first thing is that we allow iron to be incorporated within the mantle, as we know is the case for Earth and other terrestrial objects, as we've heard in earlier talks during this conference. And that's going to systematically increase the density of the mantle and thus the planet overall. We also include high pressure phases. So this is post-post-perovskite and post-post-post-perovskite and post-post-post-post-perovskite. From these sources in the literature here, even if you think that this exact sequence of transitions to post-post-perovskite, et cetera, might not be your personal belief system for the phase transfers, the important thing is that overall, as you get to higher and higher masses, you're going to achieve higher and higher pressures, and there are going to be phase transitions that occur that don't occur within Earth's interior. And that's going to systematically increase your densities. And finally, we do allow the mantle to be molten, which is going to decrease the density of any hot planets. As we move on to the core, the key thing is up here, the HCP iron. We use a new equation of state, a new formulation for the equation of state, which is known to extrapolate better up to high pressures in the terapascal plus regime than what is typically used in the literature. And the net effect is to systematically increase the density of planets. We allow the core to both be solid and liquid. Some models in the literature assume everything's solid. Some models in the literature assume everything's liquid. We let it be either with a melting curve from the literature, and we allow light elements to reduce the melting temperature. And the presence of light elements, of course, reduces the density. So I've presented to you one of many models that exist that do that. So why trust this one? Because it independently, mostly you can ask if you care, agrees with seismology for solar system objects. So here is REM1D, the reference Earth model 1D. You might be familiar with PREM. This is a similar effort to that. And this is the interior of Earth on the left for all of Earth, and on the right, we're just looking at the upper mantle. And here is our model. You can see that the radius of the Earth is replicated to within 0.15%, which is, as far as I'm aware, the best in the literature. And importantly, the moment of inertia coefficient is also reproduced to a similar degree of accuracy. If you look at other interior structure models, it's somewhat common to have a systematic overdensity in the core and a systematic underdensity in the mantle. And those two things might cancel out for Earth, but that doesn't necessarily mean that they're going to cancel out for all bodies. So it's important that you're not only getting the radius right, you're getting this moment of inertia coefficient correct, which is telling you about the interior structure. If you look even more, you can see that the transitions between the mantle and the core and all of the phase transitions in the mantle are agreed with seismology quite well, including that 660-kilometer transition, which became infamous yesterday. But we don't just want to look at the Earth, because the Earth is only sampling one part of parameter space. We might have a great model for Earth, but maybe it doesn't work for an exoplanet. Unfortunately, we don't have this level of data for exoplanets, but we do have a seismometer on Mars. And here is our model compared to Mars. You can see that there are several different forward models generated for Mars's interior here. These are the different black lines. They have the same parameters, except for what's changed is whether I use the known from the literature composition for Earth's mantle or Mars's mantle and Earth's core and Mars's core. And you can see overall, for this family right here, where we include a Martian core composition, we agree quite well with Mars's interior for a radius error and a moment of inertia coefficient error to within 0.5%. So if we go down and we about an order of magnitude in mass, and we still have a good replication of the radius and the moment of inertia coefficient, we can be somewhat more confident than we would be otherwise that we can go up an order of magnitude in mass. And you might be wondering, what is causing this big change right here? Well, in this case, the core is solid, and in this case, the core is liquid. So even this inclusion of light elements, which is one of many different things included in the model, can have a very significant effect. Of course, this changes the radii, but as we are familiar with magnetic fields, this core state is actually a very key thing to understand about exoplanets. But it's not just Earth and Mars. I have validated the model on Mercury, Venus, Earth and Mars, as we talked about, as well as the Moon and Europa. And you can see in all cases, we get radii and moment of inertia coefficients that match with the literature to within 1% or 3 sigma. And if we just exclude ourselves to Earth-like objects, it's even better than that. So with that, I will leave up my summary here. The paper has been submitted, but it's not available yet. If you want me to email you whenever it is submitted, just scan that QR code there. I'll just email you when the paper's submitted. Don't worry, I won't add you to the advertisement mailing list. And up there, you can get the mass radius curves I talked about. Thank you, and I'll take questions if you have any of them.
Amazing, very impressive. We have one question here and one here. Here, Giacomo. And there was one here.
Hi, Bennett. Thanks for the talk. Rob Calder, University of Cambridge. So,
oh, okay. Thank you.
Yeah, so thanks for talking about those interior structure models. Really interesting. Once the paper's published, will these mass radius curves be publicly available?
They're already publicly available. So they're just on GitHub at that link right there. We will update that GitHub link with whatever feedback we receive from the referee, and the goal in the future is to always have the mass radius curves be publicly available.
Perfect. Thank you.
All right, thanks. There was one question here, I think.
Hi, Skinner. David Rice, University of Wisconsin-Madison. Promised I would ask you a question. So, at what point would you like to expound? Are we over-indexed to the solar system for our exoplanet models?
I would say that we're probably already over-indexed to the solar system. So I would frame what I'm trying to do here as not necessarily breaking out of that fact that we're over-indexed to the solar system. I'm trying to do the best that we can within the problem that we already have, which is our over-indexing to the solar system. So if all of our models are just looking at the solar system, let's get the solar system as good as we can. And then from that baseline, we can start expanding out to exoplanets. So in the next paper that I work on, I would like to talk about sequestration of water within the interior. So if you have any ideas about that, please come talk to me later.
Cool. We have a question. You have a question? Okay, yeah, sure. Let's do it.
Hey, Claire Yuan, ETH sir. Thanks for the very interesting model. I'm glad you're making this publicly available. I think that's going to help a lot of people. So my question is, when you're reproducing Earth, so we don't know the composition of Earth's core, right? We just know its density, but this is like an outstanding problem. So I'm wondering how you decided what compositions to use, and then more broadly, for an unknown exoplanet with an unknown core light element composition, how much of a problem is that going to be? Like, what kind of uncertainty will that cause in trying to retrieve just the bulk iron content of a planet?
Yeah, sure. So this is when I said that it's mostly independent. It's independent where it's possible to be independent, which is largely has to do with the compositions. We have other ways of measuring the composition of Earth's mantle besides just looking at it. But for the actual core composition, that is fit to the seismology. So we have the constraint from the bulk density as well as the size of the jump here from the inner to the outer core and where it happens.
I just mean like if it's carbon or hydrogen or nitrogen or
okay, yes. So we here are assuming that it's oxygen and sulfur. It might not be oxygen and sulfur. So what we have as the parameters here might just be the amount of oxygen and sulfur that you need to replicate what it actually is. That's certainly possible. To answer the second part of your question, as much as this is very impressive, at least to me. Volumetrically, the core takes up a very small portion of the exoplanet as a whole. So the entire thing going from fully solid to fully molten is going to be less than 1% difference. So I think it's important to get right as good as we can, but I wouldn't sweat it too much if it turns out for exoplanets that we're over-indexing on the solar system and don't understand that. That's more relevant for the mantle.
All right, thank you. Let's thank Bennett one more time. All right, and our next speaker is Billy Edwards from Astron. You have 10 minutes, Billy.
Thank you. Okay, good afternoon, everyone. My name is Billy. I'm from Astron in Leiden here in the Netherlands. And today I want to take a little bit of time to talk to you about an upcoming mission called Ariel, and to go over some work I've been doing to look into the potential to study rocky exoplanets using phase curves with this mission. So I want to start by giving you an overview of what Ariel is. Some of you know a lot and are very involved in the mission. Some of you have maybe never have heard of it before. That's okay. You only need to know two things about Ariel for this talk. The first one is the wavelength coverage. So you can see on the screen that Ariel has 6 instruments. There are 3 photometers and 3 spectrometers. These operate from 0.5 to 7.8 microns. Unlike maybe HST or JWST, which you're used to, these all operate simultaneously. So what this means is once you point Ariel at a target, you get this data all in one go. So you get that continuous coverage from 0.5 to 7.8 micron in one shot without having to go back and take extra observations. There's also no different like operating modes. There's no different filters or gratings or anything like that. So all of Ariel's data is essentially exactly the same. The only thing that ever changes is the exposure time, which is of course based on the brightness of the target. The second thing you need to know is that that Ariel is dedicated to exoplanets. So I've written at the bottom of the slide the aim of Ariel, or at least this is not like the official ESA quoted aim of the mission, but from my perspective, this is what Ariel will aim to do. And this is a meticulous chemical survey of exoplanetary atmospheres, with the idea essentially of enabling demographic studies of atmospheres. So demographics at the moment we think about in terms of the bulk parameters, mass, radius, period, things like that. And the idea is to study enough planets that we can then start to do this with atmospheres. So what I've been doing is having a look to see, okay, how does Ariel compare to other facilities that have been used to study rocky exoplanets? So you can think of this kind of axis of increasing knowledge of rocky exoplanets. On one side, we have Spitzer, which is kind of the first space-based instrument that was used to do phase curves of rocky exoplanets, just using a single photometric band. And then maybe on the other side, you have JWST. And so for a comparison, I chose the MIRI LRS instrument. And the question essentially is how does Ariel compare to these two facilities? Where might we expect this to be on this kind of axis? And so that's what I'm going to focus on today. So to do this, I did lots of modeling of Ariel data. So I used something we call the tier 1 resolution. I don't have time to go into exactly what all these different tiers are, but essentially all you need to know is this is just 7 spectral points. So instead of doing spectroscopy, we're essentially using the white light curves from the spectrometers to give us 7 spectral points, or in this case, 7 phase curves. They're all taken at the same time. And then these are modeled at the cadence of the saturation time of the instruments, and then adding some Gaussian scatter based on, we have a tool called Ariel Rad, which essentially models the expected performance of Ariel. And so we can use this to get the uncertainties on each of these data points. And then, of course, model the actual phase curves from these planets. So using just the standard kind of things of having the flux from the day side and the night side, using the reflected light as well, and then adding in transits and eclipses. For all of the phase curves that I did, I assumed the dayside temperature was equal to the maximum theoretical dayside temperature, that there wasn't a hotspot offset. I put the night side temperature to be at 50 Kelvin just to avoid mathematical errors, and then, of course, set the geometric albedo to be 0. So when fitting these phase curves, I was fitting all 7 of them simultaneously, and having Gaussian priors on kind of the system parameters, so the stellar parameters, the orbital parameters, all those sort of things, and then very broad uniform priors on the actual parameters that we care about, the night side temperature, the day side temperature, and so on. And then because I wanted to do a kind of comparison to say, okay, how does this potential Ariel data compare to JWST, I did exactly the same thing, but then used the JWST ETC to do the MIRI observations. So what I did was I selected, I think, 6 planets of different temperatures to say, okay, for these different kind of classes of objects, what is the comparative kind of performance of these two facilities? And so what I found is this. So this is a plot of the dayside temperature against the uncertainty you would get on the dayside temperature if you took, in each case for JWST, is one phase curve. So those are the gold kind of hexagons. And then in red, blue, green, and pink is 1, 2, 3, 4 aerial phase curves for each of these 6 targets. And so what you can see is that for lower temperatures, even if we stack many observations with Ariel, it seems that a single MIRI phase curve will do a better job of constraining the dayside temperature. But as you move to hotter planets, in just a single phase curve or maybe a couple of phase curves, Ariel is giving kind of compatible performances to JWST MIRI. Now, I was slightly surprised by this. Maybe you are as well, given how big JWST is and that sort of thing. And I think one of them, I think it's based on a number of things. One of the key things is wavelength coverage. So if you think about a blackbody emission spectrum for different temperatures and how much of the flux each of these instruments would be sensitive to, you can create a plot like this. So this shows the temperature versus the amount of captured flux by each of these instruments. And so what you see is MIRI is essentially very, very sensitive to cooler objects around 500 Kelvin is where it peaks. But then because it's got this just longer wavelength coverage, as soon as you start to get hotter planets, then you're not capturing the kind of bulk of the emission from the planets. Whereas with Ariel, as you go to these hotter targets, because we're going all the way into the visible, you do get that extra flux. And so if you go down to, thank you, sort of things that have like 2000 Kelvin, you're only getting maybe 5–10% of the flux from MIRI being actually detected. So this maybe explains some of it, and there's a few other things going on. But I'm sure also what other observers in the room are thinking is, okay, these simulations are very nice, but are they overly optimistic in terms of the uncertainty that we could get on the dayside temperature? The answer to that is, of course, yes. So what I did was, reality is always more annoying than your simulations. You know what you put in. And in here, there's no systematics, there's no stellar variability, nothing like that. So what I did was compared one of the MIRI simulations I did to real data. So I did this for GJ367b. So there's a paper published 2 years ago now by Zhang et al. And this is on the left, the real data from JWST MIRI. On the right is the simulated data that I have. And if you look at the constraints that we seem to get from the dayside temperature, in the simulated mode, I only get constraints of 55 Kelvin. On the real data, they weren't as good. They got 90 Kelvin uncertainty on the dayside temperature. And this is a factor of about 1.64. So I say, okay, my simulations are clearly optimistic, but this seems to be the sort of a factor by which I need to increase my uncertainties on this parameter for this particular planet. So then when I went to sort of build, okay, if we wanted to do a phase curve survey with Ariel, what might that look like? You need to do kind of 2 things. One of them is to get an idea of what observable you want to have, and the second is a requirement on that observable. So I decided to go for just constraining the dayside temperature. So we've seen a number of plots like this of the substellar temperature versus the R, or the measured dayside temperature divided by the theoretical maximum dayside temperature. So I said, okay, I want to just populate this diagram as best as possible and have an uncertainty on the dayside temperature. I had a look at all the error bars on there and said, okay, the LHS 3844 one looks quite nice. It's about 5%, so let's aim for 5% on all of these targets. And in each case, the uncertainty that is coming out of the simulation, I'm timesing by 1.7 to account for the systematics and all those other things that you don't have in that simulated data. And so what this ended up looking like, and this was very kind of naive target selection, but these are all fairly dense objects, so above sort of 75% of the density of Earth. And in about 1,000 hours, Ariel could do a phase curve of 25 different planets. Some of them required 1 phase curve, some of them 2, to get under this sort of 5% uncertainty on the dayside temperature. And so this is what that distribution might look like. Now, to any observers in the room, again, if you went to JWST and said, hey, can I have 1,000 hours to go and study rocky planets, they might well say no. But luckily with Ariel, because it's a dedicated mission, we have a lot of time available to us. So the Ariel science time over the prime mission is about 24,000 hours. And the plan for Ariel is to study around 500 exoplanets, or at least 500 exoplanets. So if you were to take a really naive kind of target selection methodology where you applied the same amount of time per target, which is an awful idea. You should never do that. That's not what we're going to do. But that works out as about 48 hours per target. So an average Ariel target will have had 48 hours spent on it. And if you look at the time required per planet for this kind of phase curve survey, that's only 40 hours. So actually doing these phase curves of these rocky planets is not actually an expensive observation for Ariel. And so potentially we can push this even further, do different objects or repeat phase curves to look for variability and all this sort of stuff. So as a rough equivalence, I haven't shown any comparisons to the Spitzer data, so you just have to trust me that in one Ariel observation, we seem to get much, much better constraints than the Spitzer data, even though there was sort of 10 or so Spitzer IRAC phase curves. I think this is very expected given the narrow wavelength coverage of Spitzer and all the issues with systematics and so on. And if you compare the constraints on the dayside temperature from what's predicted for Ariel to JWST MIRI, it seems like for these cooler planets, MIRI is going to be much better at getting the dayside temperature. But once we get into these hotter planets, lava planets, that sort of thing, the Ariel actually could give very good constraints on the dayside temperature. I will note this is all very preliminary. There's lots of caveats about the modeling and so on, and the actual equivalences for the other parameters also may vary, and I've not had time to fully kind of look into that yet. But this gives you a rough idea of the kind of relative compatibility between the different things. And for that, I will then go to my summary slide, which is to say, okay, if we have this axis of increasing knowledge of rocky planets, Ariel should hopefully lie closer to the kind of JWST side, provide another instrument to study rocky planets with. And so, yeah, with that, I will thank you for your attention and happily take any questions. Thank you.
Thank you. Do we have any question for Billy? We have one in the middle here. And one here also.
Hi. Me?
Yeah.
Okay, hi. Thanks, Billy. Hannah Diamond Space Telescope. I'm curious with all this time if you've considered doing phase curves of non-transiting planets.
I've been thinking about looking into it for several years and never quite found the time to do it. I think, yeah, that could be a really useful thing to do with Ariel because you get like the short wavelength data, which should just be the star, and the long wavelength data can then be the variation of the planet. So I think it's something we would like to look into, yes.
Very cool to do. Yeah.
Thank you. Brandon, next. Can you pass the mic back? Then we had one here.
Hello, nice talk. Brandon Coy, Chicago. I'm wondering if you played around with, so one of the issues of why we don't use the shorter wavelengths is because the contrast ratio starts dipping really, really low, like into the ppm, potentially even parts per trillion. So I'm wondering how your results change if you try to include maybe sort of a noise floor of some given amount, like 10 ppm or 5 ppm, to be a little bit more realistic on what we can do at the really, really short wavelength range.
Yeah, so that's a good question. So actually, although I included them in each of the fits, the visible photometry, you essentially don't see the eclipse, and it's not actually providing any useful constraints in most cases. Maybe as you get to really hot ones or you get to things like 55 Cancri, then you're getting to that point of needing a noise floor. But I think otherwise it's not actually at that noise floor yet. But I agree, yeah, I think especially for 55 Cancri, it's a useful thing to put in, and it's something we're considering of having, 20 ppm noise floor to avoid being like overly optimistic on the performance.
Yeah, at the same time, I think albedo in the visible is also a very powerful constraint that Ariel might be able to provide.
Potentially, yeah, and I think it will be just the brightest few, I guess. Or you have to go and take, many observations and hope that it's not variable.
Yeah.
But yeah, potentially.
Thank you. We had one question here. No? Okay. Well, no more questions. All right, then we can go to the next talk. And the next talk is for, let's thank Billy one more time. I don't know if it deserves it.
Thank you.
Thank you, Billy. Okay, the next talk is Conor Chevroll. It's from Universidad Diego Portales in Chile. And this is going to be the last talk of the session.
Good enough. Do I have to hold this? So hello, everyone. I'm Conor Chevroll. I recently finished my PhD and started a postdoc at Universidad Diego Portales in Chile. And today I want to talk about some recent work we've been doing in characterizing the atmospheres of smaller and cooler exoplanets using ground-based high-resolution spectroscopy. So one of the primary ways we can study exoplanet atmospheres is through transmission spectroscopy, where we can measure the chemical composition. So in the near infrared, where our work is primarily focused, common molecules such as H2O, NH3, and CH4 all show prominent spectral features, meaning observations in this wavelength range can probe their abundances. There are several high-resolution spectrographs in this wavelength range, Carmenes, Cry-Res, Igrins, and in the future Andes on the ELT. And all of these are positioned on large ground-based telescopes. At the resolutions these instruments can achieve, typically 50 to 100,000, the broad and overlapping molecular bands, which all too often are degenerate at lower resolutions, can be resolved into individual spectral lines, such as shown here for CO, giving a unique spectral fingerprint for each chemical species and allowing us to achieve high confidence chemical detections. So this method of high-resolution spectroscopy has allowed us to achieve huge success over the years for hot Jupiter planets. Alongside multiple chemical detections, constraints have been placed on abundances, temperature pressure profiles, how cloud and haze properties similar to in low res, but also on atmospheric dynamics and isotope ratios, with the individual spectral lines providing a real rich source of information. But before we can access that information, we first need to isolate the planet spectrum from the telluric absorption, which is orders of magnitude stronger. This is sort of the main challenge for observations of this kind, particularly in the near infrared, where the telluric contamination is particularly severe and variable. And to correct for this, we often make use of the fact that the orbital velocity of the planet is much greater than that of the star, meaning the planet spectral lines are Doppler shifted significantly through the observations relative to the stellar and telluric lines, as shown here in this animation. We can then use a technique such as PCA, principal component analysis, to remove features which are stationary in wavelength, isolating the planet signal. But this dependence and reliance on the orbital velocity of the planet and inefficiencies in methods such as PCA has typically limited this technique to larger and shorter period planets such as hot Jupiters. But everyone here is interested in observing rocky planets, including those rocky planets on longer period orbits with cooler atmospheres, perhaps even in the habitable zones of their host stars. And so we really want to be able to observe these smaller and cooler planets at high resolutions from the ground. And there's some very good reasons for wanting to do this, like alongside and in addition to existing efforts with JWST. As I've already mentioned, high-resolution spectroscopy offers complementary information to what can be achieved in space, and the ability to resolve the individual spectral lines and break the compositional degeneracies will be really important in the future for high-stakes detections of, for example, biosignatures. But also, high-resolution spectroscopy is better suited and more able to probe the atmospheres of cool, cloudy planets with high-altitude cloud X, and can go some way towards breaking degeneracies with high stellar activity, helping to mitigate the contamination from M dwarfs. So with this in mind, we want to push into this parameter space of smaller and cooler planets, and we perform a case study observation of the super-Earth L9859d. Now, this is a challenging target given its small size and small radial velocity change during transit. The planetary parameters are shown here, which place the planet near the edge of the radius gap and with a density which could be explained by a rocky planet with a hydrogen atmosphere or a water world with an equal composition of rock and ice. And this is one of 5 planets in a system orbiting a nearby and very bright M dwarf star, making this system observationally favorable for atmospheric follow-up. We have 3 transiting super-Earths in the inner system, with 2 more planets in the outer system, discovered more recently using RVs. And one of the reasons this system is interesting is the potential for active volcanism on the inner 3 transiting super-Earth planets, given their non-zero eccentricities and associated tidal heating. And this has been somewhat supported observationally by previous results. L9859d has been observed previously in transmission using JWST NIRSpec, finding an atmosphere with the relevant spectrum shown here on the right-hand side. Performing a retrieval on this spectrum reveals tentative, although unconfirmed, signs of sulfur-bearing species, H2S and SO2, which, if confirmed, may be indicative of this active volcanism consistent with the tidal heating. It's also worth noting that SO2 has been identified in the atmosphere of the B planet in this system. So on to the current work, we observe the super-F L9859D in transmission using the high-resolution spectrograph IGRINS, which covers the near-infrared H and K bands. So whilst a detection of H2S in the H band is certainly possible here, unfortunately, SO2 has insufficient lines in either the H or K band to facilitate a detection in this work. Going back to the radial velocity, I'll mention again that this planet has a very small change in radial velocity during the transit, making the telluric correction very challenging. To try and mitigate this, we use some work which we published a couple of years ago now, where we simulated observations of temperate sub-Neptunes and found that actually you can achieve chemical detections in the atmospheres of longer period planets from the ground if you observe sufficient out-of-transit spectra, as shown in this plot here. The reason this works is that the out-of-transit spectra provide the necessary contrast between the telluric lines and the planet lines to replace the contrast that was previously provided by the changing Doppler shift of the planet. So in this work, we take a data set with a significant number of out-of-transit spectra compared to the in-transit spectra. And on to the results. The main result is that we do achieve a chemical detection or inference of H2S in the atmosphere of this planet. I suppose this may have been the first inference of a species in the atmosphere of a super from the ground if I'd spoken an hour ago before Engin. But still, it demonstrates the feasibility for observations of this kind using ground-based facilities, current ground-based facilities with 8-meter telescopes. On the left-hand side here, we have posterior, which is fairly well constrained and consistent with the planetary parameters. And we calculate a detection significance of just under 4 sigma. On the right-hand side, we again recover the planet signal using the cross-correlation framework, fitting the transit duration on the y-axis rather than the more traditional KP, finding this is a better parameterization for the longer period planets. So exploring a model grid for H2S models, we find that the data prefers a cloud-free atmosphere consistent with the previous JWST observations. We can also explore model grids for the molecules we do not detect, such as CH4 and NH3, calculating the preference of the data for the absence of these molecules as a function of cloud top pressure and chemical abundance. And this allows us to estimate upper limits on the abundances of these molecules. For example, for cloud-free atmospheres, we constrain subsolar abundances of CH4 and NH3 to 3.6 and 4.6 sigma respectively, and find additional evidence against the presence of H2O at a more tentative 2.8 sigma. So putting this all together, this planet and the other planets in this system have been modeled both prior to and in light of the previous JWST observations, with the implications of confirming the presence of the sulfur-bearing species discussed across a number of works, which I've tried to list at the bottom here. In short, the detection of H2S in the absence of other molecules such as H2O and CO2, which we find here, suggests a disequilibrium production of H2S, likely due to active volcanic outgassing from the surface, consistent with the tidal heating expected from the eccentricities. So I'll leave my summary slide here with the main takeaway being the current feasibility and future potential of the characterization of super-F atmospheres using ground-based facilities.
Right. Thank you, Connor. I think we have one here. We'll keep you for the last two.
Hi, an amazing talk. Thank you. Did you apply injection recovery tests to see if your data set would be able to recover the injected H2S signal?
Yes, so we did. So in the paper, we've done injection recovery tests for all different molecules. And we find that the H2S injection is consistent with the signal to noise we recover for the H2S we actually find.
Thank you. Okay, I will have to give the questions to the lock, I guess. Okay, you want to start? And then you can have the other one.
Hi, Limbo Christmas, Uppsala University. Great talk. Can you say a little bit more about this very exciting not KP visas diagram?
So no, it's wrong way.
This one, yeah.
Yeah, here.
What that is.
Yeah, so for these sort of longer period planets where they undergo a very small change in RV during the transit, it's very difficult to get a constraint on the KP. So you often find that if you plot KP cis, it will just be degenerate in the KP. So we thought, oh, it was kind of pointless plotting that every time, right? But what you can do is measure the number of frames that the signal exists in and try and constrain that to see if it's consistent with the transit duration. So showing here that the cross-correlation signal we find is constrained to the transit and therefore likely not like a stellar signal, which would be in all the frames. Yeah.
Cool, thank you. Last question.
Claire Guillemot, ETH Zurich. Thanks for this is super exciting results. I'm wondering if you can say anything about the mean molecular weight of the atmosphere and if it has to be low enough to imply that there's some H2 gas. And I'm asking because H2S is what you would expect from outgassing from a magma ocean underneath an H2 atmosphere. So this is what we showed in the paper led by Harrison Nichols, and that'd be really cool if that was true.
Yeah, so I mean, in this work, we haven't done like a full retrieval where we're constraining the mean molecular weight. The aim of this is sort of to do a feasibility study. So when we've done our model grids, the constraint abundances and stuff, we fixed a lot of parameters and just got like basic things. I think doing a retrieval is definitely the next step and to try and calculate the mean molecular weight.
Thanks.
Okay, thank you, Connor. Okay, with this is the end of the session, and please join me to thank the speakers. We have been overflooded with the flash talks, so we are not taking any flash talks anymore. This is finished. We'll have the last session. I think tomorrow, Tim, is the last session for the flash talks. Yes. And now we're just doing a break of an hour, and we have the breakout session just after. So have coffee.